doping. Then characterization techniques. I have characterized my material by UV visible spectra, IR spectroscopy, XRD, SEM, FESEM, EDS, and PL. Then first one, UV. That UV excitation, that UV spectra, I have getting the absorption energy at different energy levels. For the host 5.04, for the EU 4.41. Then IR spectroscopy, I have getting the vibrations, different vibration structure at the for the various bonds. So that various bonds, I have cleared that the absorption of my material and my doping elements are completely absorbed in my material. Then SEM, that SEM, I have getting the SEM at at various sizes. But that picture is not clear that my particle is a completely nanomaterial, so I have taken the FESEM images. So FESEM images, I have taken that I have taken the material at various ranges from the first one at various so sizes. The pictures are also not clear, so I have taken at the images at the nanometer level. But at the nanometer level, this image at the 200 pointer, that last one middle image at the nanometer levels. At the nanometer level, there are someone hard particles I have clear. That means that at the 200 nanometers level, it is also not clear images. So we consider at that my particle size is below near about 100 nanometer. After that, I have taken that XRD for the perfect particle size. By taking the my data with IC DD file size as 969001420, and after that comparing that file, I have getting the trigonal hexagonal structure. By using Debye-Scherer's formula, I have getting the particle size 28.776 nanometer. After for the absorption, I have taken the EDS, that EDS spectrum of electronic composition of the my host material, and so that by using that EDS, I have getting the clearly absorption of my all the materials of BA, AL, SI, O, and EU. All that images absorption I have getting clearly. After that, I have getting the PL. After in that the excitation spectra, I have getting one highest peak at 30 nanometer. I have taken this highest peak 304 nanometer for the emission wavelength. Then for the after that the emission spectra, I have getting that 3 peaks, one at 450 nanometer, another 510 nanometer, and another is near about 600. There are very high intensity peak at very low intensity peak at the 510 nanometer and 600 nanometer, so I neglect this and only consider one highest peak of highest intensity 450 nanometer. So I am taking this for the PL. Then after that the imaging coordinator, radiation imaging, I have find out the color coordinators. That graphical spectra of the this is the graphical spectra of the color coordination. After that, I have getting the highest peak, that A point is exhibit the strongest blue color with the coordinators with X and Y coordinators. That means my region is nearly about the visible and nearly visible region. So we can conclude that the our sample is can be used for the solid state lighting or for the preparation of the LEDs. Then conclusion is the synthesis of the europium doping in our phosphor, that X-ray indicates that our structure is hexagonal structure. I have getting the different absorption by using the UV, and PL in highest intensities at 510 nanometer signifying that phosphors are suitable for the lightning, and our color coordinates are completely in the visible and near visible region. And our CI color coordinator diagrams also indicates that our sample is used for the solid state lightning. This is the references. Then thank you. Then questions. Yes. Okay. Okay. Yes. Yes. Yes, sir. That formula. Yes, sir. Doping, sir. Sir, by comparing that reaction,
Not relation. Doping and substitution are totally different.
okay.
There is again 1 minus z, na? Al 1 minus z.
Yes.
What is that Al 1 minus z? Al 1
Sir, I
minus
have taking that my material at the very different
No, sir
composition.
is asking that Al 1 minus Z.
Yes.
So final product Ba2 minus X, Al 1 minus Z. What is Z?
Sir, I have taken that material, our main host materials and that doping materials, European materials at the different composition levels, at the as one
So
to
as
five.
per your
Yes.
formula, this says that actually you are replacing part of barium by the europium, not the doping.
No, sir. I have taken the host material completely as the that first reaction. It is a host reaction. Host reaction is same as it is, and I have taken that host materials also doping. Sorry, concentration at the different levels also, and the doping element as the europium. This is also at the different concentration level. So I have taken all this reaction at the very different composition levels. So after that, that
No,
different composition
whatever
levels.
you are saying and what formula you are written, that is not matching.
see there is
So
a
this is
dx.
the simple formula. Means if I deleting that 2 minus x 1 minus z, it is the simple formula. And if I have putting that the x values are different concentration values 1 2 or whatever in case of the concentration level, then I have getting the different reactions. So after different concentration, different x y z values, I have getting the different reaction. So I have taking my powder sample at the different reaction. I have collected that that reactions nearly about 40 to 50 reactions, and so I have characterized all that 40 to 50
No,
reactions.
we are not talking about that. Just we are talking about the formula substitution doping.
Yes.
And at the beginning, you said that this particular material is the high crystalline. I don't understand. High crystalline means in what context you are talking about? I know that crystalline and amorphous, but high crystalline means what?
Sir, I have referred many papers.
No. High crystalline means what?
Okay. Uh, I have another question. You showed XRD of your material Ba2Al2Si, barium aluminum silicate, right?
Yes.
Have you captured XRD after your doping? And you showed that there have been systematic approach for
Yes.
towards doping.
Yes, sir. I have taken the XRD data, and after that the
No, it is not yet confirmed. XRD is not captured for that, right?
yes,
The
sir.
doped material.
Yes, sir. No, sir. Only host material capture.
No, then how sure are you about the structural changes and several correlations will be missing, right?
Yes. Sir, I have doped that europium also in my research. Europium also, then cerium also, and the combination of the europium and cerium also. So I have characterized that my sample for most of the character
No, but
only for
the
the host.
data presented here does not have that information.
Okay.
See, once you are coming for the presentation in the Raman hall, you assume that audience should know something.
Sir, my material transitions are in blue region. No, European, for the European it is not only in blue region. The my sample is emitted in the blue region. Sir, European only that for the yes. Sir, I have only may name two that the emission is only visible to near visible region, and not about the exactly perfect the color is that green, blue or whatever. It is the emission is nearly about that 500 to 600, but the wavelength it is in the visible to near visible range. That means our out of output is that the outlet wavelength is in the visible to near visible range. Yes. 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 Yes, sir, my aim is not to completely find out the how much what is the color exactly. My aim is only to find out the it is the only visible to near visible range. So, yes, sir.
What is the range?
Sir, 400 to 600 nanometer. Yes. Yes.
Okay.
Yes.
Ma'am, I have one question.
Yes.
Which element is replaced by the europium when you are doping? Is it replacing the barium or aluminum?
No material is replaced. Only dope in that material. In that my host material.
Means that dopant is used for making the trapping
Yes. Yes.
chemicals,
Yes.
or it is replacing?
No, not replaced. That host material is same as it is, and only dope in that European material.
Thank you.
Yes.
Yes, we
Pen
can
drive.
proceed.
Okay.
Thank you, Ms. Shweta, for your incredible work. Now, our next presenter is Mr. Vinayak, who will be presenting his research titled on quantum dots for enhanced photovoltaic devices. This topic is particularly exciting given the advancement in quantum dots for energy application. Let's welcome Mr. Vinayak as he takes the stage. Quantum dots.
No, this is not my topic.
Okay.
Huh,
So
okay, I will.
you
I
can
will.
yes.
Yes, yes. I can correct it.
Yes.
Uh, Good afternoon, everyone. So there is some small mistake in my introduction. So today I am going to present my presentation on this topic, that is synthesis and characterization of my TiO2 graphitic carbonate copper ferrite material for their supercapacitor application. So I am Vinayak Lembarkar and working under the guidance of Pragati Thakur in the Department of Chemistry, SPPU Pune. So, in my composite, my main material is TiO2. Because of having a wide application, for me, my TiO2 is a superman. So why? Because it is a very easily synthesized material. Also a cheap material also there. It is having a stability against the corrosion, and also it is a chemically stable material. But the problem is that they have the wide band gap, that is 3.2 electron volt. Because of that, they are mostly tried to get modified by simple doping method, by simple introducing some decoration of technique, and also forming a heterojunction with some another semiconductor. And according to that, they apply for this various types of application. So we are basically working for the photocatalytic application, and here I am presenting this material for energy storage. So with respect to this application, I choose a graphitic carbonate and copper ferrite with respect to their band structure. So here is this my synthesis method. So I separately prepared a TiO2 copper ferrite by using a hydrothermal method. Graphitic carbon nitride was prepared by calcination method, and then it is treated with HCl, which where the sheets was exfoliated. Then separately, on the basis of weight percentage, with respect to TiO2, I took the TiO2 copper ferrite graphitic carbonated in 100 ml distilled water and then sonicate for 30 minutes. Then I start the stirring in UV light for 3 hours, and then it is in dark room. It's continue with the 24 hours. After the completion of this stirring, I centrifuge the solution and wash with distilled water and ethanol, and then dried at 70 degrees Celsius till gets a compound dry. So to find out the crystallinity of my material, I took the XRD pattern of my composite. So this is my TiO2, which showing the anodized phase, purely anodized phase of TiO2. Here are the degree angles, and also the plane are available. And here, this is my composite, ternary composite. I start with the binary, getting the best binary product, and then it converted to ternary composite. So here we saw that the characteristic of TiO2, it shifted to lower angle, and there is a broadening of the characteristic is observed. And also the characteristic of copper ferrite is also observed in the ternary composite, which is completely not observed in pure TiO2. The next is the optical properties. For optical properties, I took the UV-DRS as well as PL spectra. So this is my black color is purely TiO2, prepared TiO2. That shows that it is active in UV region. And here, this is green line shows that my ternary composite. Here we say that my TiO2 is showing activity in visible region also. So this is a top plot of my composite. So this shows that the band gap changes from 3.3 electron volt to 2.0 electron volt, and the PL spectra show that the intensity of pure TiO2 is decreases in the ternary composite, which explain there is a reduction in the electron hole combination. It means that there is a lifetime of electron is higher compared to my TiO2. The next one is I took the FTI and Raman spectra, which shown the bond which are present in my ternary composite. So this is my TiO2. Here it is in the fingerprint region. This is for a Ti oxygen and Ti bond, and which is also present in the ternary composite. And the further parts are for the copper ferrite and the graphitic carbon nitride sheets. And here these peaks are also showing that there is a formation of titanium and carbon bond, which is correlated with the magazine, that is titanium carbon magazine. This is a Raman shift. Here we say that the black line is my TiO2 and purely TiO2, and there is a shift was observed in my ternary composite. Also, the small peaks of D and G band of graphitic carbonate are also present in my ternary composite. This hump was observed because when your material having the 2D sheets like nano sheets, that time they have the hump like structure. There is a small peaks are also found in the TiO2 in my ternary composite of copper ferrite. So the next are the morphological study of my composite. So these are the SEM images of my ternary composite. So these are the spherical are the copper ferrite, and the remaining are the 2D sheets of TiO2 as well as my graphitic carbon nitride. This is the elemental data, elemental mapping data, and this is my composition which is present in my ternary composite. The next are the TM images. Here we see that the spherical part is my copper ferrite. Here this is my copper ferrite, which is also the correlate with my elemental mapping. This is copper, this is iron. So this confirms that this spherical part is my copper ferrite. The remaining part is our TiO2, oxygen, and also carbon and nitrogen. So this oxygen is this image is counted the both oxygen which is present in my TiO2 as well as in my copper ferrite. The next is the BET analysis and VSM analysis. Because we are working on the photographic application, so we have to deal with surface activity. So that's why I took a BET of my sample. So this is the type 4 isotherm, which is basically used for those material, which is found in those material where your material showing some catalytic property, or that or the material used for some catalytic properties. This is a nano pore diameter, which confirm that my structure is pores as well as the structure composite is mesopores. This is a VSM analysis. So this is the TiO2 showing the diamagnetic behavior. So here this line showing the diamagnetic behavior, and as I increase the copper ferrite percentage in my composite, so they changes their behavior from diamagnetic to paramagnetic. The next one are the literature survey for supercapacitor. So we are working, we use this material for supercapacitor. So these are the literature, this information are coming from the literature, where we conclude that this kind of material can be used for a supercapacitor application. So currently in this presentation, I am not discussing my supercapacitor result. If someone are interested, then I can show them in privately. So in the conclusion, I conclude that I properly synthesize a TiO2 graphitic carbonate copper ferrite separately. Also the ternary composite of that material is also prepared. Then optically activity of TiO2 shown the shifting of UV to visible, and this material can be used for supercapacitor device. And also I want to share some problem which I have faced with this material, that is this material cannot be used for photocatalytic hydrogen evolution because of magnetic property. This stick with the magnetic needle. So if someone has solution on that, then we can talk on that. And I thank you. This is my references, and thank you for listening me very patiently. Yes. Yes, sir.
What is the unit of porosity? Porosity is on the x-axis or y-axis?
Sir, y-axis, sir.
Porosity is on the y-axis.
Yes.
Are you sure?
Yes, sir.
This is totally wrong.
Okay.
What do you mean by the porosity? If it is on the y-axis.
So this means that
Forget about that. What is the porosity?
this means that if these materials this characterization are taken in some magnetic field, if the magnetic field is removed, then the value shown that the magnetic behavior of my materials without magnetic this applied magnetic field.
This is
No, this characterization taken into this magnetic field, that is minus 200. Yeah, I'm telling that without in this in normal condition. So this is the magnetic field of my. Okay, sir. I don't know. Okay.
And okay, don't put the wrong result because
Okay.
choricity is along the x-axis.
Okay.
Okay, the strength of magnetic field required to reduce the magnetization to 0.
Okay.
Right? SC it is along the x-axis and it should be the overstayed.
Okay.
Okay, whatever you are saying that is totally wrong.
Okay, sir.
And you are saying this is the paramagnetic, and then for the paramagnetic why there is choricity?
Don't know, sir.
And then again for the first one TiO2 diamagnetic, if it is diamagnetic then the graph should be in the second and fourth quadrant, and your just line is parallel to the x-axis. So then how we can say that it is the diamagnetic from the result?
Actually, sir, this is actually is in second and fourth region. Fourth this.
But your graph says that it is along the x-axis, perfectly along the x-axis.
No, sir. I can draw it separately TiO2, which where I can show that.
No, you can show that one, but whatever your result shows that, it is just exactly lying along the x-axis.
Okay, it may be the value of this material, so that suppress this behavior.
Well, in some of the results, like I think it was XRD, you attribute some of the peaks you attributed to TIC, right?
No, sir. In FTR, I say.
FTIR.
Huh.
But how sure are you about that phase, presence of that phase?
This part this peaks, and here is this peak, which is correlated with my not my, but I studied what is the reason behind this peak. So these peaks are related the material which is like magazine, that is TIC material.
But the synthesis method as well as conditions, you can say, are may not be sufficient for formation of that phase. How sure are you about that? Because
Sir, like they may not means without formation of any bond between the two semiconductors, the electron cannot move from one conduction band to another.
First of all, FTR may not be very first or 100% accurate kind of characterization to attribute to the phase that you are talking about.
Okay, sir.
Thank you.
Sir.
Any other questions?
How did you conclude that your material is not used for photocatalysis?
Sorry, sir, I can't hear.
How did you conclude that your material is not used for photocatalysis? Because your compositions are very good, and I believe this will be used for photocatalysis. So, what is your conclusion? Have you tested something?
Yes, I have tested. The binary products are showing the hydrogen evolution because they are not in the system. We should continuously stirring that system. The system contains my catalyst as well as my water system, water solution. So we have to continuously stirring that material to generate hydrogen evolution. But when I introduce a copper ferrite, and they have some introduce some magnetic property, and due to that, some catalysts are stick with the magnetic needle. So which cannot be reacted, or we can say that which cannot be provide a active surface for the hydrogen evolution generation. So that's why I am saying that the result are like if all the characterization are very good, but still in the application part, because of that problem, the ternary composite cannot show the higher hydrogen evolution compared to my pure TiO2. But the binary composite of TiO2 and graphitic carbonate shown the higher hydrogen evolution from my pure TiO2. So that's why that is my problem.
For the system like photocatalytic hydrogen evolution, if you design a reactor that will contain a vertical stirrer and that will not attract your magnetic material to it, so it can be helpful for your application.
Okay, but the thing is that can we make an environment there should be a nitrogen environment should be maintained throughout the procedure.
Yeah.
So can we design a reactor like that?
Yeah, yes.
Okay.
Thank you.
Okay, thank you, sir.
Thank you, Mr. Vinayak, for your knowledgeable talk. It was truly enlightening. Now, last but not least, we have Ms. Varanjali, who will be presenting her work titled Electroweighting on Dielectric for a Microfluidic Chip Application. I welcome Swaranjali to come on stage.
Good afternoon. My name is Swaranjali Shinde. I will be presenting my presentation on the topic electroweighting on dielectric for the microfluidic chip application under the guidance of Professor Arun Banpurkar. The outline of my presentation is like this. Now, wettability generally means the spreading or adhering of the liquid on the solid surfaces. So, depending on the application in various field, we need the surfaces which have special weighting capabilities like superhydrophobic surfaces which have the contact angle greater than 150 degree, or the superhydrophilic surfaces which have contact angle less than 5 degree. So, the Thomas Young has proposed the model to show the weighting behavior between the solids and liquids. As you can see in this figure, this model relates surface energy between the solid, surface tension of liquid, and the interfacial tension between the solid and the liquid surface. So, this wettability is affected by properties of both the solid and the liquid. So, as you can see from the figure 1, the same substrate can have the different contact angles for different liquids. Similarly, the different surfaces can have different contact angles when you are using the same liquid. So, these are the permanent contact angles on the surfaces. But when we need to change the contact angle, or we need to tune the contact angle from hydrophobic to hydrophilic or the reverse, we can use the method of electroweighting. The electroweighting normally means that the change in the contact angle of liquid on the application of electric potential. For microfluidic operations, the electroweighting technique is being used. For that, we need two conditions. The first one is we need the surface with low surface energy so that our droplet can be moved without any hysteresis. And the second is that we need the liquid with the highest surface tension value so that we will have the greater contact angle, greater initial contact angle. From the common polymers that are being used for electroweighting, Teflon, Teflon has the lowest surface energy, which is 20 millinewton per meter. And from the liquids that are being commonly used, water has the surface tension value of around 72 millinewton per meter. So this duo is being chosen for most of the electroweighting applications. So motivation is that these chemically smooth surfaces can give contact angle of up to around only 120 degrees Celsius. But the maximum limit we can achieve is around 180 degree. In this case, our droplet forms almost the spherical shape, just like the pears. So we have seen in the nature that the liquid does not weight the lotus leaf surfaces. This happens because there is microstructure is present on the leaf surfaces, which is called cilia, which suspends the droplet partially into the air and does not allow it to come in the actual contact of the surface. This is why the lotus leaves are considered as super hydrophobic surfaces. So in being inspired from this lotus leaf structure, we can increase our contact angle on our chemically smooth polymers by incorporating some microstructure. For this, we have proposed the commercially available and ready to use nanoparticle dispersion. With this, we can achieve the contact angle of greater than 150 degree. Once our substrate is ready, means which was the second condition, that we need the highest contact angle for electroweighting. Now we need the method where we can tune the contact angle from hydrophobic to hydrophilic and reverse to hydrophobic without any permanent surface modification. So from different methods, electroweighting is the most promising method, as here we need to apply only the external electric field and we can tune the contact angle with tens of degrees without permanently modifying the surface of the substrate. And this is the reversible and reproducible technique. To prepare such substrate, we need the basic electrode. So here ITO electrodes are used. ITO electrode substrate are used, which are then coated with the dielectric layers such as polymethyl methacrylate and the parylene C. Then this layer is deep coated with the dispersion of nanoparticles using the deep coating technique at the withdrawal speed of 9 centimeter per minute, and then kept for some time for the better adhesion. Now our hydrophobic surface is also ready. To characterize this surface, we have performed the same and contact angle measurements. As you can see from the first figure, it shows the PMMA polymer with before and after the coating of the nanoparticles, and these surfaces are characterized for contact angle with distilled water. So for PMMA, distilled water shows the contact angle of around 101 degree, and when you apply the nanoparticle coating, we get the contact angle of 151 degree. Now these substrates are characterized for electroweighting. As you can see in this figure, when there is no voltage applied, the contact angle of droplet is maximum on our prepared substrate, and when the voltage is applied between the conducting liquid and the electrode, the contact angle goes on decreasing with the value of voltage. And again, when you remove this electric field, the water droplet achieves its initial contact angle. So this data can be plotted using this Young equation, and which gives the curves, straight line curves. In this equation, cos theta at u means the contact angle we have get on the application of voltage u. Cos theta y is the initial contact angle in absence of voltage, and this term is the electroweighting number, where you can where our contact angle change is dependent on the voltage. Here you can see the cycles where contact angle is changing from maximum or hydrophobic to hydrophilic and again to hydrophobic as the voltage increases and decreases. So this nanoparticle coating is now applied for the digital microfluidic device. So generally for such devices, the fluorinated materials are used such as Teflon and Cytop, but they require the post-fabrication treatments and they are very costly. So this is the prototype. This is the prototype of our device where these golden colored squares represent the individual electrodes. This is the water droplet which is sandwiched between the two parallel plates, and the voltage is applied between the upper conducting plate, which is also the ITO plate, and the bottom electrodes. This is the device setup. This is the printed circuit board, and these are the electrodes that which we can apply voltage to these individual electrodes using this Arduino and the relay circuits. So this is the actual video. This is the transport of the droplet on the electrode, and the same coating we have used as mentioned in the methodology. So we have the motion of droplet in clockwise and anti-clockwise direction. The velocity of this droplet is calculated to be 54 micrometer per second. So from this we can conclude that the routinely used fluorine-based materials can be replaced with the ready-to-use or commercially available nanoparticle coating to replace the fluorine-based materials, and we can implement this coating for the electrowetting-based microfluidic applications. Thank you. Actually, these are the references I have used. Thank you.
Any dielectric material is okay, or you want some specific dielectric material?
We need a polymer, and generally transparent polymer.
Is there any role of dielectric constant?
Yes, sir. We need because we need to keep the thickness of the dielectric minimum so that our voltage will be minimum. Can you repeat the question?
No, the value of dielectric constant.
जेवढी डायलेक्ट्रिक कॉन्स्टंटची व्हॅल्यू जास्त असेल तेवढं आपला जो लेअर आहे तो व्होल्टेज जास्त सस्टेन करू शकेल, आणि जितकं आपण व्होल्टेज जास्त देऊ तितकी आपली ड्रॉपलेटची मोशन आपण इझिली करू शकतो.
Then what about the thickness of that dielectric layer? Thickness range?
Around below 2 micron.
Below 2 micron. So here you have used the polymer.
Yes.
And what is the dielectric constant of that polymer?
Between 2.5 to 3.
2.5 to 3.
Yes.
Okay. And that Young-Lippmann equation, in the third term you have written the epsilon 0, and you are calling epsilon is the dielectric constant, right?
Yes.
Epsilon is the dielectric constant, or what?
Epsilon is the... Oh. Sorry, I have made mistake there. No. Epsilon naught is the permittivity, and epsilon is the dielectric constant for material.
Okay, then if I just do the product of the dielectric constant times the epsilon 0, so then that product is simply the permittivity.
Yes.
So that is the permittivity.
Yes.
Okay, and the 2D gamma LV. Okay.
Okay, I have a very basic question. You talked about the electrowetting and other kind of thing. Let's start with very basics. Does the density have effect on electrowetting?
Yes, sir. For higher density, we will need the higher voltage because it also depends on the surface tension of liquid.
How will that be modulated with your density?
For higher density, we will need more voltage. to move the droplet from one point to another.
So is a relevant parameter or not? That's what first question.
Sorry, no.
From the audience, is there any question? No question, then thank you.
Thank you.
Thank you, Ms. Swaranjali, for a wonderful presentation. Now, I welcome our esteemed session chairperson. I would like to extend my sincere gratitude to Professor Kolekar sir and Professor Adinath sir for their invaluable contribution in examining session. Your dedication and insightful feedback have been instrumental in guiding towards academic excellence. The examiner evaluate fairly and without bias, and their decision will be final. Now, may I request Mr. Amol Sonamne sir to honor Professor Kolekar sir. I request Mr. Vivek to honor Dr. Adinath sir. I request Professor Banpurkar sir to chair the session.
Okay, I welcome to the last session of this before lunch session. Okay, I hope so. This will be fruitful because it is line with our conference theme. Okay, this talk will be presented by Dr. Rahul Maitra. Am I pronouncing correct? Yeah. Rahul Maitra is a associate professor at Theoretical Molecular Science Laboratory at Department of Chemistry, IIT Mumbai. Actually, we met at one particular conference and he delivered a very interesting talk on quantum computation, because we talk always in terms of quantum computation called quantum algorithm, but I think we don't have a quantum computer. Still we can work very fantastically. Okay. So his PhD is in, did in PhD in Indian Association of Cultivation of Science, Kolkata. And after he has several, 3 postdoctorate at RAMAN at University, Advanced Institute of Computational Science, Japan. Then at another postdoc at Cornell University, USA. Then another postdoctorate at Princeton University. And then since 2018, he is a faculty at IIT Mumbai, and he's actually chemist, quantum chemistry, and his major work is focused on development and implementation and application of novel and effective electronic structure based methodologies for ground state and excited state molecular energies and properties. Okay, and he will, I hope so, he will talk about in terms of quantum computation and little bit about how the excitement in the quantum computation and quantum field. Okay, thank you. Please. Prof.
We don't have a mic, no? We don't have a... Oh, it is over here. All right. So, and do I have a wireless mic? It's working? If not, it's okay. If not, it's okay. If not, it's okay. Yeah, it's audible, right? Yes. Okay. Thank you for the invitation here. I'm one of the few chemists who are presenting in this forum, and I'm mainly a researcher in quantum computing and many-body electronic structure theory, but more focused on molecular aspects rather than materials. So far the talks we have heard is more into materials. It's more into molecules, what I am going to talk about, and I will tell about that the molecules itself form certain challenges that we need to overcome. So the title is a bit technical. I will come to this point. What is the basic building blocks of electronic structure theory? We have one equation in our life, that's Schrodinger equation, and we don't know how to solve it. That's the entire problem. So entire quantum chemistry is about making better and better approximation how to approximately solve this equation. And why this is such a difficult task? Because the equations are too complex to be solved. And there is a curse of dimensionality. What is meant by the curse of dimensionality is that if I have, suppose, n number of possible 1 electron states, which we call as orbitals, or if you include the spin part of it, we call the spin orbitals, and you have a certain number of electrons, the number of distributions that this number of electrons can be done in that number of 1 electron states, that's exponential, the number of such states. For example, if I have 21 electrons into 43 1 electron states, I have about 10 to the power 12 number of different determinants, antisymmetrized determinants, which are basically spanning my Hilbert space. So these 10 to the power 22 is my dimension of my n electron Hilbert space. So that's the dimension of the basis vectors. So how do we do it? So essentially what it means that we start with a reference function, and the reference function may be optimized in a different way. You can choose with some n number of particle state. We choose it to be Hartree-Fock state having some certain number of electrons, and we induce some sort of an excitations, and the excitations what it does is essentially excites one electron from, this is the reference state, the left hand one, and it excites one electron from in all possible manner from all occupied to all unoccupied. Then I have the 2 electron distribution over here. I have the 3 electrons distribution over here in all possible manners up to n electron distribution in all the possible one particle states. And that entire space comprises of that many number of determinants which scales exponentially. Now, how does quantum computing actually come into play here? So you can see that the number of determinants or the number of basis vectors that we need to store in a classical computing is an exponentially difficult problem. It scales exponentially. Does quantum computer help here? So you see that if I have, say just one particle state, I can have it in 0 or 1, right? So these are the concept of classical bit, 0 and 1. What is a quantum bit, which is called a qubit, is essentially a linear superposition of all 0 and 1 spanning the entire block sphere of the entire Hilbert space for a one particle. What about for a 2 particle state? You can see the 2 particle state can have these 4 possibilities of the basis vector 0, 0, 0, 1, 1, 0, 1, 1, right? So I have 2 squared. For a 3 particle state, I have 2 cube number of basis vectors. For an n particle state, I have 2 to the power n number of basis vectors. So that's the exponential scaling. But you see that I can store, how do I store these basis vectors? That's the question that I will be addressing here. And we will show that quantum computers can actually do that at a linear number of qubits to store that exponential number of data. And that's the advantage it comes in. I will show it in a moment. Now, this is the example, for example. So suppose I'm simulating a simple molecule hydrogen. I have, say, 4 number of determinants. I have the problem size of 2 electrons in 4 one particle states. I have number of determinants 4. I require just 10 to the power minus 20 terabyte of memory. N2, I require 10 to the power minus 7. Chromium tetramer, it's a very large system. I have 7.2 terabyte of memory requirement to store that many number of determinants. If I go over to a much complex system, which is sort of a hallmark of application of quantum computing, is, for example, this iron molybdenal cofactor, which is the nitrogen fixation catalyst. I require to store 10 to the power 20 number of such determinants, which require 10 to the power 8 terabyte of memory. All right, so you can see that even for the largest supercomputers is beyond the capability, right? So what do quantum computers store what does quantum computer help here? So you can see that I can store the data at a linear number of my system size. So for 4 spin orbitals, I have 4 qubit. For 20 spin orbitals, I have 20 qubits. For 108 spin orbitals, I have 108 qubit. So over an 108 qubit, I am storing the data which otherwise require 10 to the power 8 terabyte of memory. All right, so that's the advantage we have in quantum computing. So what are the building blocks? You see that we have, one is this basically the classical, the gates. We have the NOT gate, OR gate, XOR gate, all these different gates. We have the corresponding gates in a quantum device. And these gates are called the quantum gates. For example, I have an X gate, Y gate, Z gate. There are different choices of gates, and these gates are some sort of an unitary matrix represented into an hardware architecture, and the unitary matrices are, for example, Pauli spin matrices, or any kind of a combination. Any unitary can act as the gate as long as it's feasible in a quantum architecture. And then I have these linear lines, which are the 0 and 0, these states. These are called the qubits. This is how and the qubits are sort of connected, and these are sort of called the 2 qubit gates, which are connected between 2 different qubits, and these are required what is called to bring in the entanglement among the different parts of the Hilbert space. So this is a typical quantum circuit. It is a very famous example at the very initial days of quantum computing called a Bell state preparation. So a sequence of these quantum gates targeted to create a target state is called a quantum circuit. All right, so it's a sequence of quantum gates placed in a way that I can prepare a target state. All right, so this is the overall architecture of quantum device. So I map this molecular information onto a quantum device in terms of qubits, and I can have a direct mapping. And you see that the occupied spin orbitals or the unoccupied spin orbital, that's a binary system. I can map it to a vector 0 or vector 1. It can be the spin polarization, right? The horizontal spin polarization or the vertical spin polarization. It can be the upspin and the downspin of electrons. Any binary system, I can map it to a qubit either by state 0 or state 1. And then I have something called a parametrized quantum circuit, or PQC, that does these meaningful operations to prepare the target state. And then what I have an Hamiltonian which is also qubitized from my second quantized representation to my qubit representation, and this is required because I need to maintain the antisymmetry of my fermionic operator string. And this is, of course, then eventually what we do, we take the expectation value of this wave function with respect to the Hamiltonian, which is, I will perhaps be coming in a moment, in terms of a number of repeated quantum measurements, which is equivalent to taking the expectation value of, because these are not the eigenfunctions, to get the energy, you need to take the expectation value. So the expectation value means you have the infinite number of samples, infinite replica of the same system, you measure it and take an average of it. We do the same thing here. That's the quantum measurement. And these are done in terms of what is called the Pauli words, not going into the details. So how it is done? Of course, it's not a one-step procedure. So right now, the quantum algorithms are what is known as the hybrid quantum algorithms, because of the fact that the quantum computers are faulty. And because it is faulty, because the qubits are not stable, what we need to resort to is something called the hybrid quantum classical algorithm. And what is that? It is, I have a quantum state prepared over a quantum computer here. I have a parametrized quantum circuit. I have the energy expectation value that I get by doing a repeated measurement. And then once I get this energy functional as a function of my various parameters theta, which are my the variable constraints here, or the optimization parameters, I update this energy functional by minimizing the energy, del E del theta going to 0. Rayleigh's variational principle. Okay, so it's variational. So Rayleigh's variational principle will give you the energy which is the upper bound of your exact energy. So I know that my energy cannot overshoot. All right, and then I have a classical computer here which updates the equation in a classical framework. So that's the hybrid quantum to classical mapping. And this classical updated set of parameters are fed back to reconstruct the parameterized quantum circuit once more till this circuit, this loop converges. I get an optimized set of parameter, and if my optimization converges correctly, I get the energy which is the upper bound to my exact ground state energy. That's the basic principle of it. It is much, much difficult said than done, because of the fact that one challenge is quantum noise. And the noise is, it can be that the stability of the qubits. By stability of the qubits, I mean that it has a very limited coherence time. It can be some phase leaking, so the phase information is not proper. It can be amplitude leaking, or many different, because it's an open system. It's not a quantum, it's not a closed system. Quantum computers are not a closed system. So open system means you have to take an interaction with the environment. So it's an open system. And then what we have is, this noise is what is basically killing us. So what we need to do is, we need to prepare an ansatz, which is called, this is called an ansatz, this exponential disperse, which is an unitary circuit. We need to prepare it as shallow as possible. And by shallow, what I mean is that it should scale polynomially with the number of qubits. And deep circuit means it scales exponentially with number of qubits. So I should make a very low polynomially scaled circuit. All right. So what are the problems? Even if I prepare a proper circuit, What are the challenges? The challenges is the variational landscape, and this variational landscape is something that is completely infested with what is called the local minima, because you see that there are thousands of parameters that come into the optimization process. And then if I optimization minima, which is my Rayleigh's variational principle, as per the Rayleigh's variational principle, the upper bound is at the minima of this landscape, my optimization stops somewhere in these places because it encounters a local minima. So the moment it encounters a local minima, it gets trapped over there, and you cannot drag the optimization landscape to over here. Okay, there are something called barren plateaus, and the barren plateaus are something, for example, at a particular location with a fixed set of parameters value, I don't have a particular direction of the gradient to move my convergence. So the gradient, all the gradient information vanishes with respect to all the parameters, and the optimization stops there at a flat land. It cannot just drag it to this minima. All right. So what are the options? The options is basically better initialization of parameters. So let us start with a parameter which is not somewhere very distant from this minima, but start somewhere which is called the basin of attraction. I have a basin of attraction. The lowest point is my variational minima. I start with somewhere here within the basin of minima, basin of attraction. And eventually it will get a slow descent to the minimal point. Or I can have better optimizers. That's a completely mathematical topic to work with. Now, what are the challenges here if I don't have? So there is some theory called the over-parametrization of a parametrized quantum circuit. So in short, it's the over-parametrized quantum circuit. So what is an over-parametrized quantum circuit? It says that if I have my number of parameters of my PQC, the parametrized quantum circuit, greater than a critical point, my local minima cease to exist, and all the minimas are of the same depth. All right, and what is this critical value? This is given by something called the dynamic Lie algebra, because maybe it's a physics audience, you know the Lie algebra. It's a commutator relationship, and you bring the closure relationship, and once you have the closure of the group, that's the dimension of your generators, or the dimension of your Lie group. And what happens, if you see the number of qubits at a certain number of parameters, there is a zero success probability of hitting the right minima. But then beyond the critical value, it shows a computational phase transition, and my success probability from 0 goes to 100%. So that's a computational phase transition. The moment I cross my number of parameters beyond this critical point, this is the computational phase transition. Just like any other phase transition, you have this kind of a sharp peak. So there are different ways of that, and of course, right now the way is not start with a fixed ansatz. On the other hand, construct the ansatz in a way, as you build in the circuit, you pick up what are the most dominant portions of the Hilbert space that you need to span, and design your ansatz in such a way that it hits the right kind of operators. So what it does, at each step, it optimizes, or it calculates the gradient of the energy with respect to all the parameters of the system of an operator pool. If this gradient is greater than a threshold, you grow the ansatz one step by one step. And so at kth step, I have a k number of operators in my circuit. So uk of theta, that's the length of my circuit at the kth step. You go to k plus 1th step, you pick up another operator, and your circuit grows to k plus 1, k plus 2 step, k plus 2, and that way it goes. So what it does, and at each step you are sort of minimizing with respect to all the k number of parameters that are present in your parametrized quantum circuit. This is not stochastic so far. It's still deterministic. It's still deterministic. But I will show that there comes the problem that what we start your initialization with. In the sense that this is the slide I will be explaining right now. Quantum optimizations, these are called heuristic. By heuristic, it means that there is no guaranteed convergence to your global minima. It's a trial and error, hit and trial method. So if you, at every kth step, if you parameterize if you set all the parameters random with random initial value, you get stuck somewhere here. All these shots, all these red, yellow, blue zones, these are all where my actual global minima comes over somewhere here, even below. So these are all where it got trapped in these local minima or the barren plateaus. What this kind of an ansatz can do is that it's like these rabbits or the rats digging through the ground and tunneling it through the ground to make a hole in the very deep in the ground. So this is called burrowing. So if I have a landscape which is full of local minimas, this kind of a growth ansatz, it can burrow through the landscape to your local minima, or at least somewhere to your local minima. But again, this is heuristic. It does not analytically guarantee convergence. All right? We have our own methods. Have the same signature. Instead of growing one ansatz at a time, we grow by a group of ansatz or group of operators at a time to grow your parameterized quantum circuit. All right, so you can see that it is completely infested with swamped with global local minimas and barren plateaus, and we need to sort of burrow it underneath these global minimas to hit you. But the problem is that you still need a very, very large number of parameters, which perhaps is still not realizable in the current noisy hardware, because the moment you need more parameters to burrow it through, your parameterized quantum circuit becomes so deep that it exceeds the current coherence time of your device. All right. So what do we do? So can we have these multiple objectives that we must satisfy to kind of make it realizable in the NISQ device, and NISQ is, by NISQ it's an abbreviation, it means the noisy intermediate scale quantum devices. So our current devices are all called the noisy intermediate scale quantum devices, and the name itself suggests that it's noisy. So we need to reduce the number of parameters. At the same time, so we cannot hit that critical point where I will expect to see the phase transition. I would be avoiding the local traps by sort of burrowing it through. And of course, we should not take exponentially large number of repetitions of the circuit or quantum measurements, because then anyways, it will be too long a process. So what we do here, we do something where we take hint from something called an adiabatic decoupling. What is that? And this is something that we started in 2011-21 or somewhere. And that is something that comes from a field of mathematics called synergetics. What is synergetics? Synergetics means if you have a multivariable system, how the parameters or the variables behave with respect to each other. Do they have an inherent correlation among the variables the way it optimizes? All right, so this is the field developed by Wolfgang Haken called synergetics, and we take help from synergetics. What it says, if we see even from a classical computing, if I have this kind of a nonlinear optimization process, you can see that, and this is your this is the variables which are sort of arranged from largest magnitude to the smallest magnitude. You see a gradient here. So some text, and this is the iterative steps embedded as individual discrete time steps. You see that some of the parameters which are the very large magnitude, they are taking a much longer iterations to reach to a fixed point. These are much shorter. Can we decouple the system in a way that my system will essentially near the phase transition will be dictated by only this set of parameters, this smaller set of parameters, which I will be called as the principal parameters, or theta p. And the rest of the parameters, which are much larger space right here, which has a much shorter time scale of equilibration, I will call it as an auxiliary parameters, and let me restrict my optimization process only within the principal parameter subspace. Yeah, of course. So what I am going to do is, even if I go in a wrong path, I will do some corrections which will take a vertical digging to my path. That's what I do. How do you know that it's a wrong path? Wrong path means I will encounter a flat line. That's why I will identify as a wrong path. I will show it in a moment. But yes, it's a very, very important question. It's not heuristic in a way that on the fly I will realize that this is the wrong path because my gradient is vanishing, and then I will activate some auxiliary subspace correction that will, without burrowing it through the landscape, I will take a vertical dip to my global. Okay, so that's the entire idea. All right, so what does this mean? Even this thing is that if I have a phase space, by constructing this entire set of parameters, and I have a phase space constructed by only this little bit of principal subspace of my parameters, I will get the exactly same heat map of my phase space. So it ideally, this small space replicates your dynamics, the optimization process. All right. So given that, what I conjectured here is that, let me say that the adiabatic approximation, and it's a conjecture, I cannot prove it, don't tell me to prove it. Let me say that the variation of these auxiliary parameters, let it go to 0. And I will freeze the variation of the auxiliary parameters in the characteristic time scale of my principal parameters, which take a much longer time, like a Born-Oppenheimer approximation, those of you who know. The nuclear motion is much faster. I freeze the nucleus, check the electronic motion, then freeze the nuclear motion, then again change the nuclear motion, freeze it, move the electronic motion. So if there is a very distinct time scale of motion, you freeze the motion which has a much longer time scale, and at this fixed clamped position, you do the short time scale evaluation. So I have a dynamic decoupling, which is called the adiabatic decoupling, which freezes my motion of the auxiliary parameters. And then my synergetics tells me, the moment I have an adiabatic approximation, let me write down my auxiliary parameters as a functional of only the principal parameters. Now see, from my entire system, my auxiliary parameters is gone. And remember, this is auxiliary parameters is the largest subspace. My the auxiliary parameters itself are the functional of my principal parameters. All right, so I have built up a synergistic relationship in between this set of parameters. And then I have essentially 3 questions now to address. Is how to choose and optimize this principal subspace? What is the corresponding functional relationship that maps my auxiliary parameters to my the principal parameters to my auxiliary parameters? And how to incorporate still the effect of so many auxiliary parameters, because they are smaller in magnitude, but they are too many in number. So their collective effects are very, very large. So what we do is, the first part, how do we select the principal subspace? Again, you can take it any fixed depth answers, you can do it with a variable structured answers, you can start with a gradient of this energy functional. And I'm not showing the mathematics, this comes out at an approximation to be a commutator. And if you see that the commutator, that means the very value of this gradient is greater than a threshold, you tell this that this is my principal parameters because it has a much larger gradient, that means it has a much longer time scale of variation. And I can fix by a threshold how much I will go to choose the principal subspace. Or I can choose it by some chemistry inspired way, that I start with a fixed cutoff and say whatever the parameters at my 0th perturbative order has value greater than this cutoff, I call that my principal subspace. Both are equally good, has their own pros and cons. You can see this paper actually from us. Now, once these principal parameters are known, what I have, I sort of activate what is called the parameter shift rule. So the parameter shift rule says it's a completely generic rule, and I don't need to invoke which kind of parameterization I have done to represent my parameterized quantum circuit. And the parameter shift rule with the applied adiabatic approximation that ensures that my auxiliary parameters now can be analytically written down. You see that here you won't see any subscript of A with theta. All the thetas are labeled by P. So I have mapped my auxiliary parameters theta A only in terms of the principal parameters theta P. So I have, that means I have this mapping. And once I have this mapping, what I need to do, how do we incorporate these so many auxiliary parameters into my energy functional? And for that one, what we need to do is essentially that we devise something called an auxiliary subspace correction. All right, so my optimization space is still within the primary subspace. I have something which has called the auxiliary subspace correction that includes the energy effect in a non-additive manner to the energies that I obtain within the principal subspace. And so if my optimization stops somewhere, what the question he has made, if my optimization stops somewhere, and it can very likely that it will stop somewhere, I will have an additional auxiliary subspace correction that will take me very deep to my global minima. All right. So this is the form. I'm not going into the details. So what it comes out from some little bit of algebra, of course, this requires a lot of algebra here. What I have is that you see that this is my energy functional coming out of the principal subspace, optimized principal subspace. And I have a fixed depth. By fixed depth, that I mean that it does not require any additional quantum resources. It does not require any additional measurement. It does not require any additional CNOT gate or any additional quantum device. I can have an scalar correction to this optimized energy coming out of the principal subspace. And I can have a different level of sophistication. I call it the auxiliary subspace correction with scheme 1 and scheme 2. The scheme 2 has more terms, and of course, if you had more terms, it will be more accurate. The advantage is that no additional CNOT count. So my get depth is fixed just to the amount I require for my principal subspace. No, it's an one-step additive energy correction. No optimization required for theta A, and can be executed in parallel. Use the parallel quantum architecture. So this is a sort of a grand scheme. We call it ADX-ASC. AD stands for adiabatically decoupled. X is the method of your choice. You can choose it anyway. Fixed depth answers, variables depth answers, whatever way you'd like to choose your X. Followed by ASC is the auxiliary subspace correction. That means I have a quantum state prepared on a quantum computer. I choose my principal parameters by some gradient informed way or non-gradient informed way. I optimize it within the principal subspace. I have a mapping that maps these optimized principal parameters to my plethora of auxiliary parameters, and it is not a one-to-one mapping. It is a composite variable of the auxiliary principal parameters that are being mapped to your auxiliary parameters, and then we enforce the principal parameters energy functional plus the non-iterative correction. All right, so this is the grand scheme. It's a plug and play model. Choose X to be any method. Say choose X to be a very state-of-the-art method, which is sort of gradient informed way of calculating these energy functionals. And you can see that now your question is, I can answer your question. You can see that up to this part it is, I still have not activated my auxiliary subspace correction. I have chosen my principal subspace. Principal subspace is allowed to grow, and here with the number of parameters, it sees a flat land. I cannot see it's going down anymore. My optimization stops here on the fly. I activate my auxiliary subspace correction, and instead of now burrowing it through the energy landscape at the cost of a very high number of parameters, it just takes a vertical dip. Very, very near to my global minima. Instead of coming out this way, which will be coming here, which will perhaps require some hundreds or thousands of number of parameters, I just take a vertical dip from here. Same here. The moment I encounter a local trap, on the fly I can identify that, just take it vertically. Okay. The advantage is that my parameter is only 14 parameters. I can simulate a molecule, say for example, BH2 or lithium hydride with only 15, 20 parameters. It's very, very shallow, extremely shallow. Just a 1 point correction, say for example, over the energy, potential energy surface, you can see the red color, which is some way of choosing the principal parameters. The moment I enforce adiabatic decoupling, auxiliary subspace corrections, you see that the corresponding dotted red line, which is about an order of magnitude or 2 order of magnitude more accurate. This is energy difference in a log scale. All right, over the potential energy surface. And of course, at each step, you can map these parameters. Each step you take one principal parameters, map them to your auxiliary parameters, and initialize your auxiliary parameters from this set of mapped parameters. That way, I am starting my optimization process from within this funnel of attraction, or the basin of attraction. So you can see that what my ordinary, there is no auxiliary subspace correction here, by the way, which otherwise would have taken so many number of function evaluations. I can do it half of it, just by better initialization. So see, this is a field that is coming out of quantum science, quantum chemistry, some sort of engineering, because that part will come later, and of course some part of mathematics and nonlinear dynamics. So it's a very, very interdisciplinary set of research. How much time do I have? Huh? 10 minutes, sorry. So I will perhaps not go much deeper into that anymore then. I choose any other method, and yeah. Yes.
So
The more parameters means you have a longer tail of optimization.
no, I'm not asking about the number of measurements, but the measurement protocols themselves.
Yes, it requires it depends on number of parameters, of course. Your question is with respect to number of parameters?
No, not number of, the nature of the measurement protocols. See, you're doing quantum measurements, right? So I'm asking that, so that will also bring in its own errors.
Yes.
So the kind of protocols you have, will that change your optimization results? That's what I'm asking.
So, yes,
And
it
where
does.
does that where does that enter into your?
Oh, okay. So this is currently at the, I will show the device applications, but these are more into a simulator. It's more of an algorithmic development. So you have an associated spam error, as it is called. The spam error is a state preparation and measurement error. Now, in general, that if you do infinite number of measurements, you will have, of course, a much better average. So just like taking an expectation value of your thing. If you do a certain number, you will always have some error. But of course, there are some hardware techniques like, say, error suppression, sampling error suppression, gate twirling. All these things nowadays can be done to have a very small variation of your error around a average value. So in general, yes, quantum measurements, they depend on the kind of hardware we use and the kind of protocol we use for these measurements. It can be statistical and it can be exponentially many. That gives you always a better result.
So that doesn't enter in, because you see,
No.
that doesn't enter.
No, I have not included any error channel here as of now.
Because that will also make a difference, right, to your optimization procedure.
That will. So that requires a realistic hardware. That will require a realistic hardware application. I will show that in a moment. All right, if I, instead of doing a variational optimization, can I say that my parameter space, let me decouple my parameter space from my reference space to my external space. Let me decouple it. And now, instead of having the energy parameter optimization, I will optimize this off-diagonal matrix element between phi naught and the set of the set of excited determinants by an effective Hamiltonian, U dagger HU. And I invoke this adiabatic approximation. I still don't have a variationally upper bound because of the fact that I'm no longer optimizing my energy, rather than I'm minimizing an residual. And of course, the residual minimization and your energy minimization, they are not identical, but at a limit they are identical. Till that limit, there is something called a Gershgorin circle theorem, which gives you the difference between these two. So what it does is essentially prepare the state, evolve the state in a quantum device, select the set of operators you would like to choose, and instead of minimizing the energy, construct the residue of this off-diagonal matrix elements by doing some quantum measurement and minimize this residue with respect to the parameters. All right. And I invoke the adiabatic approximation I still am able to write because I have an underlying parameter shift rule, which is a completely global rule, and it does not depend on which kind of parameterized quantum circuit I am working with. I still can write my adiabatic, the auxiliary parameters as a subset of, as a functional of my principal parameters. And if you see my results now, you can see that the moment okay, let this be the one. So if I have a conventional projective eigensolver, it's not a variational eigensolver anymore. You see, this is my optimization trajectory with respect to the number of residue evaluations, the purple one. Just like what I showed before, I do it in a subspace. My energy is still very, very high. I activate my auxiliary subspace correction, takes a dip, goes over to the exact value. I don't need that many number of, instead of 350 measurements or number of function evaluations, I can do it around 140-ish. Okay, so that's the kind of saving in the coherence time over the computer and saving over the realistic. So I have to have a very, quantum computers will not solve everything. You will have to design your algorithm accordingly. And at least in the next few years, when we still far away from fault tolerant quantum device, there is no way that you will have to be able to handle noise, and you will have to be able to handle your algorithm in a way that can be sort of implemented on the noisy quantum devices. Of course, I'm not going into all these results for the sake of time. Let me drop these ones. Let me drop these results. And you can see that here, this is application in a real device, quantum device. And the moment I am talking about a real quantum device, you see that there is nothing called a convergence, right? Because this is just garbage. You are just oscillating randomly. It's all quantum noise. And that's the shaded region is the standard deviation. And I can still see an energy dip here. I can still see an energy dip, but you can still see that there is a substantial amount of noise. So the red solid line or the green solid line, they are actually an average over this entire trajectory. I have done 50 experiments. And if I do the same thing without invoking my adiabatic decoupling or auxiliary subspace correction, you see that the result is somewhere here. If I increase my gate depth, my result is on the rooftop. Okay, it's not in the scale even. I can, reducing the circuit depth, I can bring it here. And at the end, when my optimization, there is something called optimization, but say, let's say quote unquote optimization ends, I can invoke an auxiliary subspace correction over this averaged value. And that's the post-iterative mapping auxiliary subspace correction, takes it even lower. Still this much of error, and I rely on the engineers to bridge this gap, to come up. This is real experiment. So I rely on the engineers to come up with better devices out of my territory now. Okay, let me skip this one. All right. Yeah. Oh, this one? This one is the corresponding noiseless. Corresponding noiseless value. If I do it in a simulator where I don't have any kind of a device noise, that's the exact value I'm going to expect with this parameterized quantum circuit. Okay, so I'm still pretty far off. I'm still pretty far off. It's somewhere 1.9 something, 99, and I'm somewhere here perhaps at 1.85. And this is way beyond your chemical accuracy. We want it much better. And if I synthetically devise my noise, I can show that this method actually, so what I mean by synthetically devise, I can cook up some noise channels. And if I attenuate my noise strength, you see that all these plots take a lower shift, downward shift, and come close to my exact value with an artificial noise channel, which is 1 order of magnitude less my ideal device noise right now. All right, let me skip this one. Okay, so what I conclude here, I believe I have 2 or 3 minutes, so let me conclude. What we expect is up to 1 or 2 orders of magnitude more accurate results from the state of the art. I have the adiabatic decoupling. The adiabatic decoupling ensures that my parameter space is decoupled. I can post-territory hab and post-territory correction through my auxiliary subspace correction, which takes me closer to my exact value, without invoking, and you can see that every time it takes a vertical dip with respect to parameters. That means it perhaps avoids all the moment it encounters the barren plateaus of the local traps, without introducing any additional hardware resources, it just takes a particle digging to your global minima. That's a drastically reduced quantum resource. It can escape the local traps in certain cases. Again, this is heuristic in the way that I cannot have an analytical convergence guarantee. But 99% of the time from my experience, it is accurate. But again, this is trial and error. And of course, I have a new initialization technique for faster convergence such that my parameter space starts within the basin of attraction. So what next? We are sort of in collaboration with IBM. So we are a sort of very close connection with IBM, and so many of my students are actually working in IBM as interns over there, clubbing the method. So we are actually going to have all these IBM's machines accessible to us. And they are promising us a less noisy quantum hardware in next 5 years. So I'm relying on that, the noisy hardwares. Very recent development, Majorana chip from Microsoft, maybe a bluff, I still don't know. Microsoft has this habit. So I don't know, but at least I'm in close connection with Google and IBM, and they are promising us showed something on hand. And of course, we have many collaborations with different industry who are sort of came up with, particularly the startups who are came up with this quantum computing as a tool for their drug designing and material discovery process. And I am sort of working in collaboration with them. These are some papers. I mean, you can just scan it through. And this is the current group. This work is mainly done by Choyun. These are somewhat older people. Many people have left, few others joined. And these are the funding sources. And of course, we have a number of PhD positions. If any of the MSc students are available, I'm most happy to host you. Thank you. Yeah.
Okay, thank you very much, Rahul, for wonderful talk. Okay. Session is open for question and answer. Yes, yes.
Itself adiabatically. I mean, don't go directly to wave function, directly do, or not answer. Don't do direct if you don't finish it off. I mean, you do it up to a certain state, and then you get a ground state, whatever, and then start with that again, and then go till you.
See, the problem is somewhere here. Problem is that if I start with something from full parameter space, see, the problem is that if I have too many number of parameters or too many number of variables, to implement in a quantum circuit, it becomes a very deep circuit itself. So there is no way that I can implement a full parameter set of full parameters in a quantum device, at least in this NISQ era.
No,
so I will have to.
No, sorry. I'm not asking parameter. Parameter is suppose you start with
more parameters mean more gates.
Yeah, no. Let us start with a certain set of parameters, say 2 parameters. I do my variational calculation. I can finish from start to the end and get a result, okay, in one step, minimize them. But instead of that, there is a way to go adiabatically the variation method. That means don't.
There is a way to go adiabatically with variation. I mean, people are doing it. Say
that is better, I thought.
No. The point is that it requires
over
a very deep quantum circuit, and you need a very, very small time step. In principle, infinitely small time step to move adiabatically to that right state you would like to land up into. So
but I thought that if you do it for
you can in
time,
principle
you know
do it, but requires such a deep quantum circuit that it is meaningless in the this era. Perhaps 10 years after, this is the right protocol. There are methods. We have also worked on the methods which is sort of like an Hamiltonian evaluation. Hamiltonian evolution called the quantum phase estimation kind of algorithm. And these are in principle exact. These are Hamiltonian evolutions. And you move adiabatically over a given state to your global minimum. It can be done. But this is not realizable in the right now in the device. So you cannot take the quantum advantage of this superposition and entanglement. That's the problem. So I need to have a very, very shallow circuit and then invoke some sort of a correction to make up my energy. also a question on students.
Somebody else wants to ask? Okay.
Yeah.
Anyway. So what about other methods, like say if I want to do, I mean, instead of a variational method, if I were to do something like a quantum, not a Monte Carlo method, for example, would it help? I mean, to devise a, I'm not talking for quantum Monte Carlo, I mean, you know, through this kind of procedure, that a circuit Monte Carlo, quantum circuit
That can be done. That can be done. But again, I mean, the moment it finds the optimal, because you see, these are all stochastic. The moment it finds the proper landscape, this is fantastic. The problem is that it's a, you need exponentially many number of experiments to find that proper landscape.
No, I mean, see, whatever is that, I mean, the way we do the usual Monte Carlo, we have some kind of a guess value, right? Some kind of an algorithm which will decide whether you accept the thing or not. So that particular criteria, if you set properly,
you
or
can
if
do
you
that.
try to say,
You
I mean, if you
can
try
do
to
that.
define it in some appropriate method.
You can do that. In principle, you can do that. People are working on quantum version of the Monte Carlo, and this is perfectly doable. Perfectly doable. Just the fact that we sort of want to make sure that my post-optimization correction, that should be free of any sampling complexity.
Okay.
So Monte Carlo required a full-fledged sampling complexity. I have no additional sampling complexity. That's the advantage.
No, because if I want to kind of do this for correlated systems, then I mean, that's why I was trying to think about
These
it.
are all.
So in your criteria, then what about doing something like a DMRG? Suppose I were to do something
We
like a
can do
DMRG
that.
algorithm using this kind
We can do that.
because that's also some kind of a variation.
We can do that, or matrix product state.
Or an MPO state.
Matrix
yeah,
product
that's
state, right? There are corresponding answers. These are called the hardware adaptable answers or hardware efficient answers. So the idea is that you can either increase in the number of your qubits, or you can increase the depth, because see that current devices are either say the two most prominent devices. One is your ion trap hardware, or is the superconducting qubits. The superconducting qubits has a much longer coherence time, but you cannot scale it up, means you have a very limited number of qubits. Ion traps are on the other hand very short coherence time, but you can scale it up to a very, very large system, 100, 200, 300 qubits added together, and all-to-all connectivity. You don't have a particular hardware coupling map, all-to-all connectivity. So you can devise an answers in such a way that depending on whether you are working in an ion trap or a superconducting qubits, either you increase your depth, that will support for a long coherence time, or you increase in the width, that will have a short coherence time, but you can do it with many qubits, and you have some ancilla qubits and have some additional energy correction over the ancilla qubits. You can have the flexibility to increase the qubits. The problem is that you don't know a fixed starting point, and you need to randomly start it. And every time what it happens is that, and this is a particularly problem for DMRG or MPS based quantum computing devices, which is equivalent to an hardware adaptable answers, is that the answers is not trainable. The trainability issue in the sense that it always encounters a flat land. It 100% of time it encounters a flat land, and you never can, and it requires many parameters, perhaps more than the critical number given by the dynamic Lie group, but so many parameters, it is always flat land because you don't know where to start it from. So it's not within the basin of attraction.
But suppose you use your starting point so that you know kind
That's
of
what we are working on with other kind of answers.
So you kind of start with this, and so that gives you
That's
some
what we are
optimal
precisely
state,
working
and
on.
then after that use that now to do.
That's what we are precisely working on, to go over to DMRG or MPS based answers, called either the hardware efficient answers or its hardware adaptable version of it, and use our initialization strategy and the post optimization correction to see what the landscape looks like. Because without any this kind of a correction, DMRG in near future does not have any hope in quantum computing, because of the fact that since the landscape is not trainable.
And so somehow that means you have to figure out how to model the density
That,
matrix
yes,
itself. I
yes.
think that you're not you're doing directly in terms of qubits.
Right.
So you have to actually think of how to put the
How to model that. We have a known quantum circuit to implement DMRG instant in terms of matrix product state.
but still there you're using states. See, for DMRG, the actual thing is you're using the density matrix.
Right. We can do that. We can do that. We can do that. But usually it is done in quantum computing. It's done usually in matrix product state formulation, because that's perhaps easy to map to a qubit. But
That's what I'm saying, that starting point there, even if you use matrix product operators, you're using that still in terms of qubits.
I use
so
still
I'm
in
saying
terms.
that one, but if you look at, think of the MRG, the foundational part, it's not really in terms of states, it's in terms of a density matrix.
Right,
and
right,
then
right.
I minimize
Right,
the,
right,
I
right,
kind of
right,
optimize
right.
the dimension of your density
Of course.
matrix. So somehow then I should not think in terms of qubits, but
I know that, but how do you
yeah, that I
map the
directly a density matrix have to get.
auxiliary indices or
No,
your
no, I'm
these
just saying that
indices are
probably that
too difficult to, I mean, you eventually need a matrix product state representation of it, otherwise the DMRG as is, so you need tensor network state.
Yeah, you need tensor networks.
I need tensor network state. So that's the problem we have it, and we tried it, not hopeful, at least the DMRG in itself, but I had a secondary question. The DMRG is by itself a linear scaling method. What do we gain by doing it in a quantum computer? These are exponentially scaled methods.
It allows you to do perhaps faster. I don't
That perhaps doing it faster, but doesn't save in terms of scaling, perhaps. Perhaps my thought, but we are trying to do it. I'm not sure whether it will go on. And we are also incorporating into DMET, the density matrix embedding theory, to go for a very large molecules, because we want to go into a material informatics. So this, yeah, there was another question over there from a student.
My question fundamentally revolves around qubits. I wanted to know how close to perfect can we make these uncorrected qubits? Like, is there any upper limit?
Yeah, I mean, there is a measure of noise, and in principle that should go to 0. Okay, so right now in some unit the 2-qubit noise is of the order of 10 to the power -2, which is pretty large to qualitatively change things, not quantitatively, qualitatively change things. So you get completely inferior theory giving a better result, and a better theory giving an inferior result, because a better theory requires a more number of qubits to implement, or more number of CNOT gates to implement, and these are so noisy that the stabilization you get from moving from an inferior theory to a superior theory, it gets destabilized by the noise. Okay. So right now unless you, but well, IBM is promising us that in next 5 years they will give us a fault-tolerant qubit. So right now what's the state of the art is something called a error correction. Error correction. So the moment you have a qubit operation or gate operation, you identify the error and undo it. That's called the quantum error correction. And we have our own methods, which is called something based on what is called the noise extrapolation methods, or something based on the graph neural network. We have our own methods which are called the error mitigation, that I know that my circuit has produced faulty values. How do I take it by some classical post-processing? How do I take it to my zero noise value, expected value? So this is called error mitigation, and this is a more of a analytical and numerical technique rather than a hardware technique. Error correction is a hardware technique, but it still requires 5 years, I believe, to go over there.
So as of now, correction is not really helping much.
Correction is helping, but well, it comes at a price. It comes at a price. Because correction means you require to implement more gates. The gates will undo the effects.
So the number of gates is increasing.
Closing towards your coherence time limit. More gates mean. Okay. Right? So there is pros and cons on both the sides.
Thank you.
Yeah.
Interaction between the qubits or from the surroundings?
See, I mean,
what kind of different, could you elaborate?
So noise it's an open quantum system, right? So open quantum system means it has an environmental effect. So it can be depolarizing channel, it can be, say, amplitude damping, or it can be some phase leaking kind of thing. So you prepare a state. Suppose your state 1 qubit state 1 vector 1, I mean, comes with 99% probability, and say state 0 comes with 1% probability, and you allow it to interact with this, and you see that the amplitudes leaked, and your state 1 comes with a 90% probability, and the other is a other. There is a see, in principle, when you are doing a quantum measurement, you need to do it infinite number of times, right? Because that's what the expectation value tells you. You have the infinite number of replica of the system. The problem is that I cannot do an infinite number of measurements. I have to do a finite number of time. So there is a finite measurement, and this is, you cannot bypass this error. Measurement itself, I have the state preparation which might be faulty. Right? I am giving you an example at a hardware level. There was one company which was trying to build up a superconducting qubit somewhere, and that was in a first floor of a building where on a ground floor there was some party or something going on, or some banquet hall kind of a thing, and in their mic sound or the DJ sound, that vibration destabilized the qubits. So you have to keep it this isolated to this amount. Okay, so cryogenic temperature, all this stuff.
Sir, you just showed Willow, right? The chip from Google.
Sorry?
The chip from Google, Willow. So Willow has, I think, 105 qubits. And the chip from IBM, the previous one, I guess H2 was there.
Head-on.
Yeah. So it has 156 or 55 qubits.
Yeah.
So how can the Willow still outperform the H2 head-on?
At the hardware level, I don't know.
Okay.
At the hardware level, I really don't know. Because this is an engineering problem, physics and engineering problem. What I know that what is the architecture they have built in. And
So can you just
architecture is
explain
some sort of an iron trap architecture or something.
Okay.
It cannot be this much scalable using superconducting qubits. But how is the exact architecture, that I have no clue. Okay.
The last question from my side. Could you just suggest to a student that what should be our preparation? For example, because I think we cannot, or we maybe in the near future where India will build a computer or not, but it is available elsewhere. So
It is available elsewhere. It's already available somewhere. First preparation is that you need to adapt the algorithms. And not all the algorithms can be adapted this way. You'll have to figure out which are the scalable problems that can be done in a quantum device. Yeah, so which are the scalable? Say, for example, some of the problems I showed, that this nitrogen fixation, FeMOCO complex, or this kind of thing. So what are the problems that which cannot be solved classically? Because right now perhaps the classical supercomputers can do things much fast, or at least much accurate, but it's not about the fast or slow that a computer can do it. It's about the feasibility, whether a certain task can be done in a given supercomputer or not. There we need to figure out, and there are plethora of quantum machine learning problems, quantum, and it will be revolutionize material discovery, that's for sure, and your drug discovery. So these two are the near-term applications, at least to the work that we are trying to do here. Of course, there are the cryptography and communication; these are certain different areas. But at least the work we are doing here, the most two low-hanging fruits are drug discovery and quantum and material discovery. Okay. All right.
A huge thank you to Dr. Rahul Mitra for that truly engaging and thought-provoking talk on quantum subspace optimization and energy landscape borrowing. It's clear that the intersection of quantum mechanics and optimization hold tremendous potential for future. Let's give Dr. Mitra a big round of applause for his incredible insight. We appreciate the time and efforts you have investigated in this work, and your presentation was great learning. I request Professor Banpurkar sir to honor. Now we are going to take a lunch break. You are all welcome to enjoy a delicious meal and take some time to network, discuss, and recharge for the next session. Join us back for the oral presentation at sharp 2:40. The oral presentator must present on time. Thank you.
So we are starting the second slot of the oral presentation. The first presenter is Mr. Maruti Salve. And the topic will be investigation of low-cost solution process CD-TE thin films for the development of solar cells. OP5.
Hello, good afternoon. I am going to present my work entitled The Investigation of the Low Cost Solution Processor CDT Thin Film for the Development of the Solar Cells, work carried out under the guidance of the Professor N.B. Chaure. The growing energy demand is the one of the key challenge of our time. The solar energy is the one of the best alternative entitled the investigation which has enough potential to meet the CDT thin film growing energy demand. Development of the solar cells. The work carried out solar energy gives the financial benefits to the farmers as well as the homeowners. In this context, the development of the low-cost photovoltaic technologies are essential. Is the one of the best alternative entitled the solution process has enough potential to offer extreme advantages growing energy demand. Development of the low cost, fast solar energy, roll-to-roll deposition, financial benefits to the over a large area similar to the printing newspaper. In this context, the objective of development of the low-cost photovoltaic deposit are low-cost solution process is alternative. The solution process has enough potential to offer extreme advantages growing energy demand. Development of the low cost, fast solar energy, roll-to-roll deposit financial benefits to the over a large area similar to the printing newspaper. In this context, the objective of development of the low-cost photovoltaic technologies by using simple hydrothermal the cadmium acetate and tellurium oxide was used as a starting material, NaBH4 as a reducing agent, and double distilled water as a solvent. The obtained powder was deposited on a MPO substrate by using Dr. plate technique. CDT particles dispersed into the ethanol with a sufficient amount of the binder to make a paste, and that paste was Dr. bladed on the FCO coated substrate. After trying the film was filtered for a 250 and 350 degrees Celsius for 1 hour to optimize the sintering temperature. We prepared the CDT thin film for a different CD concentration of 0.02, 0.03 and 0.04 molar concentration, while mixed tellurium oxide concentration of 0.04 molar to study the influence of the composition on the properties of the CDT film. The CDT is solar cell structure, glass FTO CDS CDT AU fabricated by using solution based CDT film sintered at 350 degrees Celsius. The results and discussion. X-ray diffraction pattern. X-ray pattern of the CDT film sintered at 250 and 350 degrees Celsius as shown in figure. The XRD pattern shows the cubic polycrystalline structure of the CDTA. The XRD pattern of the CDT film with 0.02 molar CD concentration reveal the additional diffraction peaks corresponds to the tellurium. As the CD concentration increased from 0.02 to 0.04 molar, the excess tellurium significantly reduced, which may be due to the stoichiometric growth of the CDT sample. As the CD concentration increased from 0.02 to 0.04 molar, the number of the cadmium ions also increased, which reacted with the unreacted tellurium ion to form a stoichiometric growth of the CDT films. We used a WH plot to determine the average crystallite size and the strain in the film. For a CDT film sintered at 250 and 350 degrees Celsius, it was observed that the larger average crystallite size and the higher microstrain was observed for a CDT films with a CD concentration of 0.02 molar, which may be due to the excess tellurium. Under excess tellurium conditions, the small crystallites coalescence into the larger one. The segregation of the excess tellurium onto the grain boundary results into the higher strain values. With a CD concentration of 0.02, which may be due to the excess tellurium. Under excess tellurium conditions, slight increase in the crystallite size was observed for a CDT film sintered at 350 degrees Celsius, which may be due to the coalescence of the small crystals. Higher strain values. We study the optical properties to determine the energy band gap of the CDT films sintered at 250 and 350 degrees Celsius. It was observed that the optical energy band gap of the CDT films sintered at 250 degrees Celsius ranging from 1.47 to 1.52 electron volts. The lower band gap value for a CDT films with a CD concentration of 0.02 molar, which may be due to the excess tellurium. The excess tellurium introduces the acceptor states within a band gap, thereby lowering the band gap value of the CDT films. The slightly decrease in band gap value for a CDT film sintered at 350 degrees Celsius, which may be due to the increase in the crystallite size. The ACM images shows the ACM images of the CDT film sintered at 250 and 350 degrees Celsius as shown in figure. The ACM images shows the irregular grains. 350 degrees Celsius, irregular grains. The average grain size for a CDT film sintered at 250 degrees Celsius were 181 nanometer, 103 and 87 nanometer for a CD concentration of 0.02, 0.03 and 0.04 molar respectively. The higher average grain value for a CDT films with a CD concentration 0.02 molar, which may be due to the excess tellurium. The excess tellurium conditions, in excess tellurium conditions, the small grains aggregated into the larger one. The CDT film higher average grain value sintered at 250 degrees Celsius exhibits a closely packed morphology with some small voids present in the films. The CDT film sintered at 350 degrees Celsius exhibits a more compact morphology due to the grain growth. The thickness of the films examined by the cross-sectional ACM images, the thickness of the CDT film sintered at 350 degrees Celsius ranging from the 1.5 to 1.8 micrometer. The compositional analysis. To determine the elemental atomic the compositional analysis reveals that the CDT films prepared with 0.02 molar CD concentration exhibits tellurium excess. As the CD concentration increased from 0.02 to 0.04, the elemental atomic percentage of the cadmium also increased as expected. The stoichiometric CDT is thin films obtained for a CD concentration of the 0.04 molar. It was observed that the slightly decrease in the tellurium atomic percentage for a CDT film sintered at 350 degrees Celsius, which may be due to the evaporation of the tellurium. Current density figure 6a shows the current density voltage measurements. The best performance was obtained for CDT films with a CD concentration of 0.04 molar, giving rise to the efficiency of 2.91%. The CD concentration of 0.02 molar exhibits a excess tellurium shallow defects, which acts as a or contributes a recombination in the film. For a CD concentration 0.04 molar, the tellurium excess shallow defects get reduced and the collection of the better collection of the charge carrier, giving rise to the improved performance. The external quantum efficiency also measurement carried out and which agrees well with the current density voltage measurements. 0.04 molar. The conclusion: we successfully synthesized we successfully fabricated the FTO CDS CDT AU heterostructure by using solution based method. The solution processed method in this study offers a simple, low cost and the scalable approach to build a CDS CDT solar cells. We successfully fabricated the FTO CDS CDT AU heterostructure by using solution based method. The solution processed method in this study offers a simple, low cost and the scalable approach to build a CDS CDT solar cells.
In your XRD, the tellurium phase is segregated separately. Why? Tellurium T phase it is separated.
Tellurium peak act as an impurity in the CDT film. CDT, but I have studied the compositional effects on the properties of the CDT film.
If I want the pure X-ray diffraction pattern for CDT,
0.04 molar is the pure XRD pattern for CDT.
but the star is
FTO. Act as an impurity
and second thing is that how to decide whether a particular material is direct or indirect band
Study the
gap?
compositional effects on the properties of the CDT.
If I want the pure X-ray diffraction, because here you have taken directly square.
0.04
So if
molar
I
is
take
the
square
pure
root,
XRD pattern for CDT.
so what criteria is there that will give you idea that whether a particular material is really direct band gap or indirect band gap?
Study the compositional effects on the properties of the
Because you have directly taken square by assuming something else. Suppose I don't know, then what kind of criteria should be used to decide a particular material is of direct band gap or indirect band gap? Will give some idea that whether a particular material is really direct band gap or indirect band gap. And in EDS spectra, you are not shown the EDS spectra, just this one. But I am quite well worried about the oxygen contamination.
I have not taken oxygen contamination. Oxygen peaks I have removed.
You have removed it. Means there is oxygen contamination. Na? So that is a very important point. No? That's why whatever the efficiencies value you got, that's why the properties are degraded. But you did in the globe oxygen contamination.
No, only air atmosphere.
Okay. You have removed it. Means there is oxygen contamination. Na? So that is a very important point. No? That's why whatever the efficiencies value you got, that's why the properties are degraded. But you did in the globe oxygen contamination.
Thank you, Mr. Maruti, for your fantastic and knowledgeable presentation. Next, we have presentation by Dr. Vishal Bharud, who is going to talk about agriculture soil analysis and evolution through gamma ray attenuation. And I request all of you to please keep your phone silent. Thank you, Mr. Maruti, for your fantastic and knowledgeable presentation. Next, we have presentation by Dr. Vishal Bharud, who is going to talk about agriculture soil analysis and evolution through gamma ray attenuation. And I request all of you to please keep your phone silent. Thank you, Mr. Maruti, for your fantastic and knowledgeable presentation. Next, we have presentation by Dr. Vishal Bharud, who is going to talk about agriculture soil analysis and evolution through gamma ray attenuation. And I request all of you to please keep your phone silent.
Good afternoon, everyone. Myself, Vishal Bharud. I'm just going to show you some picture here right now. You can look at this particular picture and you can analyze where we are looking at. I'm just looking for the soil and agriculture soil, basically. I'm just looking at few pictures how we are going for the Vishal Bharud. concrete I'm just going to show you some pictures. concretization, and when you go for the concretization, you can look at how our agriculture soil has been spoiled. I'm just looking for the And soil how you and can agriculture see the soil basically. where the drainage water, industrial just waste looking are at going few in a soil pictures, waters, and after how getting we that are particular soil going for waters, the how you are going to get affected in the concretization, and when you go for the fertility of that particular you can crops. look at So the topic which I am going to talk on, that is the agriculture soil analysis and evolution through a gamma ray attenuation. The drainage water, industrial waste are going in a soil waters, and after getting that particular soil waters, how you are going to get affected in the I'm working at MJ College Jalgaon as assistant professor, and I have sanctioned one project from the VCRM scheme, that is a Vice Chancellor Research Motivational Scheme of 2 lakh, and my core research is nuclear cross-section measurement for the different photon-induced reactions and neutron-induced reactions. But this is the topic which I choose for the nuclear should be, some detector should be there in a college or institute. So the basic aim is to get a detector and get a agriculture soil analysis and evolution. different photon-induced. So content of my talk will be important, introduction important, objective methodology, result discussion, conclusion and some references which I use for this particular college or institute. topic. So in an introduction, attenuation coefficient, so everyone know what is attenuation coefficient, and we are looking for this particular attenuation coefficient. So as you know, in any light incident on any material, so there are some phenomena, and that particular phenomena where you have 100% photons which are inciding on any material, and how much photon you are getting after that particular incident, or reflected or scattered or transmitted. So that particular thing which can be studied by this particular photon gamma ray attenuation. So basic aim is that how you can look at this particular thing, that for the shielding, agriculture yield, soil humidity, absorption, pesticide contamination in the soil. So what physics I am looking for, that is the soil development for the some different nutrients, as we have with the hybridization for the different crops and everything for the increasing the yield. So soil varies, as I know, I stay in a Jalgaon. What is the condition of the soil? What is the condition in the Pune of the soil? So soil varies from one location to another location with their different types, that sand, slaggy clad, inorganic material, and water as well as the air. Then the main aim of my this particular project, which is not involved in this presentation, but the soil porosity, that I am going to find out with respect to this particular project. And right now what I am going to show, that is attenuation coefficient, which are directly connected to the composite materials and hence widely accepted for the characterization composition. The main aim of my this particular And the physics which I am looking for, that is the interaction of a material with the matters, or the interaction of a radiations with the matters for the different kinds, and which interaction I am using, that is the photon interaction or the gamma interaction. So the part which is where the literature survey tells me there is a very few part which is carried out for the attenuation coefficient for the soil and to study a soil porosity. So in this particular presentation, I am going to show what is the linear absorption coefficient, and then I am going to show what is the mass attenuation or the absorption coefficient, where I have this particular relations which I am going to show. So just general idea that when you have an incident photon on the particular any material, how the spectrum or something which looks. Using the Beer-Lambert's law, I know that I equal to I naught e raised to minus mu x, and this mu x is nothing but the thickness of the sample. X is the thickness of the sample, mu is your linear absorption coefficient, I naught is your intensity without a sample and I is your intensity with the sample. So looking at this particular thing, so the important of this particular project or the attenuation is in the significant interest for the industrial, biological, agriculture and medical application also. Then we are looking for the accurate value of this particular photon mass attenuation coefficient which is required, and the data which is there on the open sources is very diverse data. We should have some particular data which will give a proper idea to increase the crop yield. So these are the some applications to get into the particular field, and the important of attenuation coefficient for the soil, sand, clay, porosity. The property characterize the penetrations and diffusion of the gamma in the composition of a material such as soils are very important. So as we look at the porosity links to a roots growth. So what we apply, if you see that any plant field which does not get a water, it gets damaged. So similarly the root growth is very important for the moving air as well as water and suitable soils in this particular thing. The study of the mass attenuation coefficient in the soil for the different regions. I had choose the region which is North Maharashtra of particular regions, and I had taken some samples as well as I choose some Pune and some samples from my own hometown for this particular parameters. So main objective to determine the linear absorption coefficient, the study of the mass attenuation and some soil porosity and data generation. And I am going to use one software that is called as XCOM software, which is used for the attenuation coefficient. The methodology which I am using, that in this particular project, the 2 lakh has been sanctioned and 1,88,000. I have purchased one NAITL detector. Using that particular detector, I have studied some spectrums for this soil samples. The source which I use right now here, that is cesium-137 and cobalt 60. And europium, which I am going to use in the Department of Physics, which is there in our department. Then your methods for the nuclear technique ranging and the softwares, which is that is XCOM and ENDF. So soil fields which are collected with the different soils as you say, that is some chana soils, then you have wheat soils, some gawa soils, some maize soils. So there, this particular soil samples has been collected, and the experimental setup has been made in a such a way that you have source. The observer which I am using, that is the soil sample, and this is the detector, which I am looking for this particular detector that with a high voltage and preamplifier, amplifier, and MC with the spectrum. So what I got from this particular results, that I studied some materials first. Going to soil, I studied some materials, and that particular materials which I use, that is lead, aluminum and copper. When I look at the absorption coefficient with respect to the energy, I have got a 3 energy from cobalt and cesium-137. That is, cesium has an energy of 0.66 MeV, while cobalt has an energy of 1.17 MeV and 1.33 MeV. So looking at that particular energy, I have got the absorption coefficient for the lead, that is PB, is much more. And as you know that lead is used for the shielding purposes. Then similarly for aluminum and copper, we have a less absorption coefficient. So this study was done, and then we are looking for the detector which we are taken, that with the background of this particular detector which we have purchased, then we have a source where we get a sufficient significant peak for the cesium, then we get for this cobalt and cobalt 2 peak, and this particular spectrum which we find out with this particular attenuation coefficient. Then these are the some results which I am going to have, that as a mass absorption coefficient decreases with increasing photon energy, that is the transition of photoelectric effect and Compton effect, the physics which I have studied. Then as I already explained that lead absorption coefficient is more compared to copper and aluminum. Then beware of copper, when it increases more than 1 MeV, it has some changes, and that is due to the influence of prayer production. And this analysis is crucial for the shielding application. As I told that I have taken some material. Now I look at the soil sample which I have taken. I have taken some soil samples which are from Dhule shade. Then you have Gawa shade, muddy waters, more than 1 MeV and onion. These are some soil samples with some thickness, mass, volume and density. Crucial for the shielding application. As I have done the calculations for the attenuation coefficient and mass attenuation coefficient for the different samples. So I have got this particular spectrum analysis that what kind of absorption takes place, what kind of things happen. So this is the first part of my project, what I am going to do, and the next part which I am going to do, that is in the conclusion, that is the mass absorption coefficient for the soil for the different analysis. And here what I observed that low Z soils like Dhule and so on sir, shows the steady decrease in a mass attenuation coefficient, while high Z like a Pune and ON, they increase in the absorption at a high energy. So these were the some things which was I am going to explain. Then this is the future work which I am going to study, that is soil porosity, and these are some reference. This is acknowledgement. Senior Professor Sanjay Dole sir, head of the department, Dr. S.S. Daivale sir, then Principal Mulji Data College where I am working, the fund which they have provided, that is a VCRMS scheme, and all support while preparing the samples and everything, that is a microtron and neutron lab, Department of Physics. These are some collaborations right now I have made with the oncology department to work with the photon-induced reactions for the different cancer patients. And thank you. And all support while preparing the samples and everything, that is a microtron and neutron lab, Department of Physics. These are some collaborations right now I have made with the oncology department to work with the photon-induced reactions for the different cancer patients. And thank you. And all support while preparing the samples and everything, that is a microtron and neutron lab, Department of Physics. These are some collaborations right now I have made with the oncology department to work with the photon-induced reactions for the different cancer patients. And thank you. And all support while preparing the samples and everything, that is a microtron and neutron lab, Department of Physics. These are some collaborations right now I have made with the oncology department to work with the photon-induced reactions for the different cancer patients. And thank you. As we can take a solid, we can have some composition of like anything that we use for the increase the yield. So if we see the some elements
Thank you, Dr. Vishal, for your innovative and knowledgeable presentation. And at the end, please welcome Mr. Vishnu Gore on the stage, who will be presenting his research on titled Ion Exchange Route to Boost PEC Performance of ZNO by Architecting Type 2 ZNO NIO Heterostructure. And at the end, please welcome Mr. Vishnu Gore on the stage, who will be presenting his research on titled Ion Exchange Route to Boost PEC Performance of ZNO by Architecting Type 2 ZNO NIO Heterostructure. And at the end, please welcome Mr. Vishnu Gore on the stage, who will be presenting his research on titled Ion Exchange Route to Boost PEC Performance of ZNO by Architecting Type 2 ZNO NIO Heterostructure. And at the end, please welcome Mr. Vishnu Gore on the stage, who will be presenting his research on titled Ion Exchange Route to Boost PEC Performance of ZNO by Architecting Type 2 ZNO NIO Heterostructure. And at the end, please welcome Mr. Vishnu Gore on the stage, who will be presenting his research on titled Ion Exchange Route to Boost PEC Performance of ZNO by Architecting Type 2 ZNO NIO Heterostructure. And at the end, please welcome Mr. Vishnu Gore on the stage, who will be presenting his research on titled
Good afternoon all. I am Vishnu Gore. I am pursuing PhD under guidance of Professor S.D. Sartale. Today's presentation, I am presenting under title of Ion Exchange Route to Boost PEC Performance of ZNO by Architecting Type 2 ZNO Nickel Heterostructure. Good afternoon all. So first upon what is PEC? So here general mechanism of PEC solar cell. We can see here two electrode system. One consists of photoelectrode and another one is counter electrode, which is embedded in electrolyte. So it is externally connected, and whenever as soon as light incident, which is energy is enough to overcome band energy, that times electron hole pair is generated and electron travel through external circuit toward the counter electrode, and their auto reduction is happen, and at the same time at the surface of photoelectrode there is O2 is produced. This is general mechanism of solar cell. Overcome band energy. So for solar cell we have selected ZNO as photoanode. So why we have selected it? So see here, this is comparative band edge position of several semiconductor with respect to redox potential. Among them we have selected ZNO. So first condition for water splitting, PEC water splitting, so redox potential of water must lie within banded position of photoanode. So we can see here this condition is satisfied by ZNO. Along with that, another important properties are it has phenomenal crystal structure. It means it has hexagonal crystal structure and it having some polar plane, and because of that there is we can form various morphology of heterostructure. So that's are beneficial for PEC performance. Again, it is low cost and eco-friendly. So considering all those properties, we have selected it. But having some polar, it shows good performance. Again, it has some drawback, that is electron hole pair reduction. Electron hole pair the combination rate is too high because and eco-friendly. So considering all those properties, we have selected it. We can see here if we consider only ZNO, that time whenever light incident on it, which is energy is enough to overcome band gap potential, band gap energy. So that times excitation and de-excitation rate is too high. So we are not getting enough electron for external circuit, conduction through external circuit. But whenever we use another strategy, that is type 2 ZnO nickel oxide heterostructure, that times what happen, we can see band age potential of ZnO and nickel oxide. ZnO is N type and nickel oxide is P type. This band age position difference, that time whenever proton incident, and both within both material electron hole pair is generated. But in case of nickel oxide, there is conduction band electron transfer toward the ZnO conduction band, and those electrons are responsible to move throughout the external circuit, and we are getting better current. So that's why we have choose this strategy. Again, next part is synthesis of those material. First of all, we have taken ITO glass substrate, conducting ITO glass substrate, and by using solar method, we have prepared ZnO nanorod that is vertically grown on that ITO surface. Further, we have used ion exchange method to form ZnO nickel oxide heterostructure. First of all, we are getting nickel hydroxide ZnO heterostructure, and further annealing 400 degrees Celsius for 2 hours, we are getting ZnO nickel oxide heterostructure. We have taken 3 samples for here, one for bare ZnO and another 2 for 12 hours and 24 hours. Those are denoted as Zn12 and Zn24 throughout next presentation. So for confirmation of those material, we have performed XRD. So within this XRD, intensity versus 2 theta, we can see here in ZnO, we are all peaks we are getting Zn12 and Zn24. All peaks we are getting those indicate, those confer root side crystallized phase of ZnO, and again we are getting same peak for ZnO, but reducing intensity along the 002 plane. It is due to the incorporation of nickel oxide, but we are not confirming here nickel oxide. It may be reason that this nickel oxide layer could be thin layer or amorphous in phase. Next, surface morphology investigation. So we have taken ACM. So we can see for ZnO, hexagonal nanorod are grown vertically, and after ion exchange process, we can see their etching of surface and flex like surface area. We can see for next CT and EF, all these 4 ACM images. Again, elemental composition, we have taken EDAX. So in this EDAX, for in A, plot A, we can see only zinc and oxygen element are present, but on after ion exchange, nickel element also appear there. So we here say that there is nickel ZnO nickel oxide heterostructure for. Further optical study, we have taken UV visual spectra, absorption versus wavelength. So we can see that ZnO shows absorption is at 390, means band gap 3.17 electron volt, and further ion exchange for Zn12 and 24, we are getting blue shift. Further optical study for next confirmation, that is Raman analysis, we can see here in case of ZnO, we are getting characteristic peak. This is characteristic peak. After ion exchange, we are not getting here any peak, but after ion exchange, this peak intensity get reduced, and we are getting another nickel oxide longitudinal optical phonal mode plus transfer optical phonal mode at 1080. In case of ZnO, we are getting. Further, we have taken study PAC after ion exchange. So this is PAC measurement. First LSC, we can see that we are getting a better performance for Zn12 as compared to this red ZnO. So again, we have taken on-off plot. We can see here this sensitivity of that material. This is on-off plot for 10 seconds, and we kept here 0.5 volt constant voltage. that is consistent with LSV. Again, we have taken PSC. We have calculated PSC from this LSV plot, and we are getting performance of ZN12 1.54 times over ZNO, and efficiency also increases 1.39 times. Again, we have taken further we have taken AIS spectroscopy. Here also we are getting this plot tells us that smaller diameter of semicircle shows lower interfacial charge transfer resistance, and so we are this result also consistent with previous two. This is Mott Schottky. By Mott Schottky we have calculated carrier concentration and flat band potential and nature of semiconductor. We found that ZNO is N type and nickel oxide P type. For the final conclusion, we can say that we have synthesized successfully ZNO nickel oxide heterostructure, and our PSC performance also enhanced 1.54 times over ZNO. So acknowledgement, I am thankful to my guide Professor S.D. Sartale, and again I am also thankful to Mahajyoti for financial support. Thanks for your kind attention. And our PSC performance also enhanced 1.54 times over ZNO. So acknowledgement, I am thankful to my guide Professor S.D. Sartale, and again I am also thankful to it is heterostructure, because this heterostructure is made by ion exchange process. Ion exchange process is it is process that ZNO within ZNO zinc is get replaced by nickel oxide because of their reduction. Yes.
How do you know that?
We have confirmed this characteristic technique. This heterostructure is made by ion exchange process. EDAX we can clearly confirm there is nickel element. Zinc is get replaced by nickel oxide because of their reduction. Yes.
How do you know that?
This characteristic technique. This heterostructure is made by ion exchange process. EDAX we can clearly confirm there is nickel. We can see here this morphology, flex-like morphology occur due to nickel oxide, and again RAMAN.
Is that a confirmation? RAMAN do not show anything. If you say that last one is the peak, then I will argue that the next hump to that three there are actually.
We can see here. It look like that, but morphology occur due to nickel oxide. Yes. Again TM, by using TM we can confirm.
Nickel, by using TM you can confirm nickel. Then I will argue that the next hump to that three there are actually.
Nickel oxide. It look like that, but morphology occur due to nickel oxide. Yes. Again TM, by using TM we can confirm.
Nickel, by using TM you can confirm nickel. Then I will argue that the next hump to that
nickel oxide. It look like that, but sir, according to literature survey, we are getting this type of. Again TM, by using TM we can confirm. Nickel oxide. Okay. I think we have to take a TM. According to TM could confirm that. We are getting this type of. Again TM, by using TM we can confirm. Yes, it is airport. Yes. I think we have. There is no necessity for crystallinity. It could be amorphous, it could be crystalline. There should be some heterostructure, because whatever performance we are getting, that's sure that there should be heterostructure. Otherwise, this performance we will not get that kind of performance. It could be amorphous, it could be crystalline. That's as compared to not ZNO. Whenever we are using only ZNO, that compared to this is better. That's sure that there should be heterostructure. Otherwise, this purpose we will not get. No, we said that maybe we are not detecting that. That may be only thin layer that could not detect by X-ray, because the X-ray having high energy that could be penetrated. That's as compared to not ZNO. Whenever we are using only ZNO, that compared to this is better.
That's sure that there should be infrastructure. Otherwise, this purpose.
Yes, sir. It is hexagonal.
We said that maybe we are not detecting that. That may be the only thin layer that could not detect.
Sir, we can because of hexagonal structure.
That could be penetrated. As compared to not.
Yeah, general.
Whenever we are using only that
Sir, four dimension we can indicate on that.
Yes, sir. It is hexagonal.
We said that maybe. Fourth means
that may be only thin layer that could not.
sir, we can because of hexagonal structure.
That could be penetrated.
Sir, whenever we are taking only 3D.
Yeah, general.
Yes, sir. But upper direction we are taking.
Dimension we can indicate on that. Yes, sir. It is hexagonal.
Fourth means.
Sir, we can because of hexagonal structure.
Sir, whenever we are taking only 3D.
Yeah, general.
Yes, sir. But upper direction we are taking.
Dimension.
Sir, intensity.
Indicate that.
Actually, that intensity due to the presence of that element. X-axis, energy of X-ray. X-ray.
Whenever we are taking only 3D. Yes, sir. But upper direction we are taking. Sir, intensity.
Sir, that is SNP.
Actually, that intensity
Yes,
due to the presence of that element.
IT.
Energy of X-ray.
IT. X-ray.
Whenever we are taking only 3D. Yes, sir. But upper direction we are taking. Sir, intensity.
Sir, that is SNP.
Actually, that intensity
Yes,
due to the presence of that element.
In IT.
Energy of X-ray.
IT.
X-ray.
Model means
Sir,
experimental model.
Actually, that intensity due to the presence of that.
We have taken absorption versus
In energy of X-ray.
Actually, this is absorption edge, where it is a decline. We are taking that absorption edge.
We have taken
We are considering that absorption edge as band gap. So, okay, thank you, sir.
Actually, this is absorption.
Thank you,
edge,
Mr.
where
Vishnu,
it
for
is
your
a
wonderful
decline.
presentation. I would like to extend my sincere gratitude towards Professor Kamal sir and Professor Adinath sir for their invaluable contribution in examining sessions. The examiner evaluate fairly and without bias, and their decision will be final. Within few minutes, we are having an exciting interview session, so please be there in Raman. I would like to extend my sincere gratitude towards Professor Kamal sir and Professor Adinath sir for their invaluable contribution in examining sessions. The examiner evaluate fairly and without bias, and their decision will be final. Within few minutes, we are having an exciting interview session, so please be there in Raman. I would like to extend my sincere gratitude towards Professor Kamal sir and Professor Adinath sir for their invaluable contribution in examining sessions. The examiner evaluate fairly and without bias, and their decision will be final. Within few minutes, we are having an exciting interview session, so please be there in Raman. I would like to extend my sincere gratitude towards Professor Kamal sir and Professor Adinath sir for their invaluable contribution in examining sessions. The examiner evaluate fairly and without bias, and their decision will be final. Within few minutes, we are having an exciting interview session, so please be there in Raman. I would like to extend my sincere gratitude towards Professor Kamal sir and Professor Adinath sir for their invaluable contribution in examining sessions. The examiner
Hello, hello. Hello, hello. Hello, hello.
from the physics department.
Yes.
And I have attended many of my student seminars in this hall itself. And so I'm first of all very happy that you are doing this, having this Raman Memorial Conference. This is the 31st conference.
31st conference, yes.
So congratulations to all of
Yes.
you. So you have done
All the volunteers.
So that's the first thing. Yeah. So childhood, lot of good teachers were there in the school. And they were all very dedicated people. It was a very small school, but the teachers were very sincere. And, so I think that, congratulations. You don't get that very easily
Right.
nowadays.
All the volunteers.
And the human touch was there. So I appreciate that even in my school. And particularly in MSc, there was one teacher, Professor Govind Rajlu.
Okay.
It was a very small. He taught us applied mathematics.
Okay.
So he's somebody who's very special to me.
Okay.
And of course, there were so many others, even in my BSc and Professor Vijay. So many people were there.
Okay.
But particularly Professor T. Govindarajulu from the Madras Institute of Technology in applied mathematics, he made a deep impression on me.
So as he mentioned, he has done his master's from Madras Institute of Technology, and then he did his PhD work in PRL, Ahmedabad, Physical Research Laboratory, but his degree is from our university, so in that sense he is our alumnus of the university. So at what stage did you decide that you want to enter the field of meteorology?
Yeah, so as I said, till BSc I did from Bangalore, from the Bangalore University. It was not clear where I would be going. Because my brother-in-law, my sister's husband, he's from Nagpur University, gold medalist in applied geology. And early after his MSc, he joined the Department of Atomic Energy. So he was, in a way, he was scientifically perhaps at the highest. I mean, I was still in 12th standard at the time. My sister got married. And so he was a kind of inspiration because he knew. So he was applied geology, joined the atomic energy. And now, of course, he's a retired scientist. He's also now in Bangalore.
Okay.
So this is how I got to know that you have to. So science is a good field. I mean, of course, we didn't have a big background in our home and science and other things. So it was any regular normal family. And our childhood also, I grew up playing with all kids, playing flying kites and spinning tops. Roadside cricket, so nothing very fanciful. And like any other, I was in the middle. I was not in the top student. I was neither in the top nor bottom, somewhere in the middle. So this was my career. But I think after BSc I got good marks, and then my mother used to tell me you have to study, do well. So she was a big push. You have to want to achieve something. To study well. And then I applied for MSc, and Bangalore University at that time I got statistics, MSc in statistics. Then I had applied for this Madras Institute of Technology in Chennai, where they have a 3-year BTech program after BSc. Now they have changed. Now they have a 4-year BTech after 12th. So I could not get admission in the BTech program. But then I also applied for MSc, applied mathematics, which was a very good course. So I was fortunate, I got admission. So that's how my admission into MSc happened. Now they have a 4-year. And so it was a tough course, and these teachers were extraordinary teachers. HOD was one Professor RAMAN. He was very good in numerical. He was a tough person. And Professor Govind Rajulu, I remember. And there was Pratibha Patil. She's a Maharashtrian. Of course, she studied, she had education in Karnataka also. She would talk about classical mechanics and all those things.
Not our ex-president, other Pratibha Patil.
She is also Pratibha Patil. I hope she listens to me. Yeah. These are all wonderful teachers, and we had a good, and the course was very good, and there were only about 10 or 12 students in the class. It used to be like a school, MSc, just pin drop silence, every Monday test. So test means I used to get shiver. It was a nightmare now when I start thinking. And some of the abstract subjects like, topology and fun, it was going above my head. I used to, but I was good in programming and numerical analysis. So these were, I appreciated also all those things, how to solve those equations. And so that was the kind of first time I got the inspiration. So MSc I did well, and maybe I topped in the class also. It was a small class, so from Anna University. And usually what happens is because it was an engineering college, everybody gets placement after BTech. Either electronics or IT. It was not information technology, it was instrumentation. It was very strong instrumentation. And electronics was there. They all get placement. And aeronautical was there. And our former president, APJ Abdul Kalam, is from MIT, by the way. So it was a very famous institute. Even now it is a good institute. So all the BTech fellows that get into get jobs, they will go either HAL, they all get private companies. MSc people, they are kind of left over. So you really don't know what to do. So I still remember one day there was a blood donation camp somewhere. So I also went and gave blood donation. Then I came back and then I met, because everything, the course was over. Everybody was going for vacation. I met one engineering student. He told what you are going to do. I told, I don't know, I have not got anything. But MSc, let me see. But they had all found jobs. He told, you see, there is an advertisement in newspaper about physical research laboratory, PRL. Course was over. It's also ISRO laboratory, it comes in the Department of Space. Why don't you apply? If they have a PhD program, you get scholarship. MSc. So I just sent my cover. Immediately I sent it. I don't know whether they will call me for interview or physical research. So I just applied. I also applied for IASC Bangalore. I cleared their exam, PhD entrance exam. Why don't you apply? But I attended in applied maths and computer science and maybe aeronautical department. I was not selected. So I was not selected in interview. But PRL, when I applied, they called me for interview. And so I considered it extremely lucky. So first time I'm going to Ahmedabad from Chennai, I went there, attended the interview. I was very confident. But when I saw all the people, coming from IITs and big place, I thought so this I am telling you.
Which year it was?
This was 1987.
1987.
So I still remember the dates. I left, and there was another interview on 19th for ONGC. I wanted to get a job immediately. And that interview was in Chennai on 19th. And 15th, I am leaving Chennai. This was 1987. And 17th is the interview morning. I still remember the dates. And the train starts Navjeevan Express from Chennai. On the way, somewhere in the monsoon, somewhere it was rain. It was rain and caused flooding, and the train route changed. So they came via all this down and Nandur Bar. And I still remember that. And train reached after 12 hours delay. So I was supposed to reach on 16th evening. It is reaching there on 17th morning. Okay. So before that I had spoken to Professor Govindraj, my mentor. Sir, I told sir this PRL interview is there on 17th and 19th ONGC interview is there. So I want to attend both. He told you cannot do both, you attend one. Okay. Unless you fly, you go by flight. Okay, but whatever little money I had, I thought like so there used to be a book called Trains at a Glance. I don't know how many. So 15 rupees I purchased. Which train is going, everything I calculated. I took that and let me see. I went by unless you fly. And when I saw and so I reached on 17th morning, PRL. So then I see, I went already. Interview is going to start at 8:30, and I'm just entering the gate. I went to the security gate. So security guard was some Tamil South Indian. Immediately saw my Then he told I want to freshen up. So I freshened up in the security itself and went for the interview. So I've not booked any accommodation, nothing. Then I saw all these students, from IITs. So I told I finished. So this is also gone. ONGC is also gone. So this is what happened. Then I went to the board. Then I self-impressive all big professors from PRL. So I've not booked any accommodation. Young boy. Then I saw all these students, young adult of course. So I told I attended, but I was very confident. So I attended the interview. So this is what they asked me. So I told sir, I have not. Physics I have studied only up to BSc. Now only you ask me in mathematics, applied mathematics, I can answer. Okay. So they asked me a few questions. Then I told I derived some of the. There was also Professor Kadkikar who was there here. I remember. He's now in Panchavati. He was also in the board of my interview. Okay, I was very confident. I answered. I derived. Then I told. I saw some people. They are there for 2-3 days. They have completed first round, second round, everything. I cannot attend so many days. So I told whatever interview you have, you please do today. I want to go back. That's why you want to go back. So I told I have not completed my project. So I have not completed my project. I have to go on 19th. 3 days. That was partly true, but not fully true. It was not on 19th. I told I have to go on 19th. So I told whatever interview. Then they told okay. You wait outside. That's why you want. And then I was waiting outside. And Professor A.C. Das came. He told that yeah, we did not ask you any question in physics. Partly true, but not fully true. It was not on 19th. I told them, okay, fine, sir. Okay. So they called me and they asked me some questions. I immediately some question on simple harmonic motion. So whatever I told, they were very happy. They told you now you can go. Okay. And something on optics, Newton rings and something I told. I told you can take your, you can have lunch, you can collect TADA and you can go. This is how. And then I thought then I'm out by 1:30 from PR. Then where to go? Now I have to, trains are not. And actually the Navjeevan Express to Chennai has left in the morning. Okay, so if I have to attend on 19th, I have to reach there on 18th. This is how. And now if I wait for 18th, then Navjeevan, I cannot reach. Right. So I told I will go to Bombay. Okay, but I have not seen where is Bombay, nothing. Okay, so I told I went to the station. And then to unreserved, I was just standing in the queue. And one person came me, he told, this is how the world works. That is, you help somebody else helps you. And that was, then I stood in the queue, got a ticket unreserved, and after time, sometimes go behind and talk to that fellow. Then it became, RAC. Then after I kept on, then finally I got a seat. Then there was another Tamil fellow who was going to Bombay. So I told sir, I'm going first time. Can you please tell me how to go? I told there is one Jayanti Janata Express. Okay. You take that morning, then it will reach 18th. If you take 19th afternoon, it will reach Chennai. Okay, you have a chance. Okay, then I said okay, but then he told because of the rain they have stopped Jayanti Janata Express. What will you do? I told okay, let's do this. Then he told, see, once you get down in Mumbai, there are two Western Railway and Central Railway. Okay, so you get down in Dadar, change the platform, and then you have to go to VT. I said okay, but then so you have to go to VT. Then you are there, you will get the Jayanti. So then I got down in whatever morning, I think around 4 o'clock. I think it was Mumbai Central Railway. So I got down at 4 o'clock, went to Dadar, then changed the train, went to VT. And then I remember I rushed and they told from today Jayanti Janata Express is working. See my luck. Okay. Yes. So I go there, get a unreserved, get into the train. It started with delay. And I reached, exam was starting at 3 o'clock, the ONGC exam. Okay. So I got down at the Chennai station. Central, immediately I went to the park, park station. Took the train. Got down at Nungambakam. That's where Laila College is there. Just watched. I was there before 3 o'clock, and I had the hall ticket with me. I wrote the exam. I passed that also. No, so I think you have to try. The main message is you have to be. Sure. So I didn't go by the flight, but I went by train. Only these trains at a glance helped me.
Yes.
Then I came back after 15 days. They tell me PRL result. So you have been selected. So that's so it was. I would consider very fortunate among so many people, and that was a great place for me. And getting into PRL, all this, it was big opportunity, and which I never realized. So that is something which I hold very close to my heart.
It's very interesting to hear this entire story because you should realize how fortunate you all are. That's why I asked him the year. He said 1987. Please understand that's a pre-Google year. There's no Google nowadays. I'm sure you all are not aware of trains at a glance because you have indianrail.gov.in, right? So everything is on click. That was not the case. So even a simple thing as to go to one place, go to another place for another exam, so much efforts had to go in. And now that's not the, now you live in the era of Google Maps. So you don't have to worry, nothing. Google is there to help you in any and every way. So please understand that whosoever felt that no, we are not very fortunate, you should understand that you all are indeed very fortunate. Many things are very simple for you. But as he mentioned that nothing comes so easily, right? If not this effort, you need to take up some other kinds of efforts. So that's why it's interesting to hear all these stories. And as you mentioned, PRL was a wonderful place. So, because it's a physical research laboratory, so I think our students would love to know about it.
Physical research laboratory was started by Professor Vikram Sarabhai, the legendary Sarabhai.
That's why it's interesting to hear all these stories.
When he came, this was all in the 50s.
As you mentioned, PRL was a wonderful place. Right.
So he
Because it's
came
a
back, he
physical
went to
research laboratory, so I think our students
young
would love
person
to
who
know
came
about
back,
it.
the big dream of he and Professor Homi Baba, Sarabhai started the nuclear program. The other one space science. And, so he first, when he said that he wants to invest his money, he was a very rich person, but he had a big heart, big vision. That a lot of his money he put for research at PRL. Started in a college, PRL, and we had Professor K.R. Ramanathan, who was also who was a student of C.V. Raman.
Oh.
And who worked. So K.R. Ramanathan was there with him. So he started that, and some of his money he put in IAM, Ahmedabad. He wanted to have some management school. And there is Atira, that's for textile industry, next to
Yes.
So people say when he was the director, PRL was one of the best places, not just in India, in the world.
Oh, wow.
So he started that, and some of his money. So when you see the kind of research, it's a great place, just like TAFR, PRL was there. And so getting admission in that place was, and they were giving me fellowship 1,400 rupees, which was a big money.
That time, yes.
It was a big money. And we had a very nice hostel. And food was subsidized. And a lot of sports, which I had only played all the street cricket.
Okay.
There I could really play table tennis.
Yes.
We had a good volleyball group. So I was very active with that. A lot of friends, and you see people coming from all over India. So now you are exposed to a much bigger sports side. I was in a much smaller window.
Yes.
Now I could really play. Then you see that we had a kind of talent. Amazing. You see all kinds of people.
Yes.
So I think that is very important. So young people have to go out from their This one.
For the comfort zone also.
You
Come
have to
out
move
of
out of your comfort zone.
Yes.
That is one thing which I want to tell. And as you go out, you learn a lot. You see a lot, you experience. And that really matters in life.
Right. So like he mentioned, for example, he went from Bengaluru to Ahmedabad and it was a new world for him. He mentioned that Dr. APJ Abdul Kalam was also a student of Madras Institute of Technology. I don't know if you have read Wings of Fire. There he has mentioned when he made that journey from down south to right north by train, and he actually saw India and so many states and so many different cultures, and it was such an eye-opener for him. He has described it in details. So again, this was pre-social media era where people really didn't know what kind of world exists on the other side. So these are very, very interesting aspects that nowadays probably you all are aware of it, but still to be open to different kinds of experiences is very important, as he mentioned. And he mentioned about Vikram Sarabhai, Dr. Vikram Sarabhai. Of course, we all know about him because we have a ISRO cell in our department, but nowadays with the series Rocket Boys, some part was also shot in our own university. I think everyone knows about him, even people who have not taken up science. And these were the visionaries. They built institutes, and that is how several people could study in those places. Now we would like to know about your field, meteorology, because not everyone is very aware of it, and here we also have some MSc students. So I'm sure when he was describing his journey up to his PhD interview, some people might be thinking that okay, now because the fourth students, for them it's already February, so in 2-3 months even they would go through the same process, applying to different institutes and then waiting, and then 2 interviews are close by, okay, which one should I go to, and some such worries. So this is a field, again, you can think about it. So we would like to know about the field of meteorology.
So field of meteorology, when I joined, of course there was mainly physics,
applying to different institutes and then waiting, and then 2 interviews are close by, okay, which one should I go to, and some such worries. So this is a field, again, you can think about it. So we would like to know about the field of meteorology.
And as physics people, they don't think these meteorology people are, they are doing something, they think it's all weather forecast. They are predicting. And the arcade Lakshman cartoon will come, you predict it is the opposite.
It's always opposite, yeah.
So you are more like a laughing stock.
Yes.
And then their experimental groups work on atomic physics, astronomy, radio astronomy, astrophysics, and lot of even upper and ionospheric studies.
It's always opposite, yeah.
So, and there was a very strong geoscience group.
Yes.
And deep ocean, even on the geological studies. So it was a very vibrant research, all under one umbrella. Meteorology was a small group in that.
Right.
So you get a big exposure, because you get exposed to many things. It's not apart from so the advantage of PR is, although you are working in meteorology in a small group, so it is a very vibrant research, all under one umbrella, and that is one of the unique aspects. And you meet and all the professors were all very scholarly people, great people. And my professor was Professor R.N. Keshavamurthy, who was also director of IITM during 1992 to 96. Very scholarly man, very simple, very knowledgeable. He's Bangalore, and still I'm in touch with him. And so he is a kind of, he's also R.N. inspiration, very simple. So he taught me about, he told me there are 2 things you remember. One is the earth is rotating, the other is the equator to pole temperature gradient. This is all. He told you remember these 2 things. Okay. That is how my first interaction with him. And he's also there was big people like Professor P.R. Bisharati, who was the founding director of IITM. And he is also a student of Sir C.V. Raman. He is known as the father of Indian remote sensing. He started so they were all together with Sarabhai, Professor Bisharati, R.A. Ramanathan. So by the time he was already in his 80s when he was in PRL. And the KR, when I joined KR Ramanathan, Professor KR Ramanathan, I passed away. And also Professor Vikram Sarabhai also was also there. So all these big giants were there in PR. So that atmosphere made a big impact. And my own senior Krishna Kumar is now in US. So I learnt a lot from him. So by talking to them, and there was one Kasture, again a Maharashtrian. He did all the programming, and we have come many times to PRL. SV Kasture, and he's in Ahmedabad. So although it's a small group, and there was Dr. Satyan, who came here later on into WMO. So I learned a lot. This small group, that's when I started learning, because I played mathematics. He did all the programming coming to this field. So Professor Keshamurthy would tell me, you read this Holton book, 6 chapters, and give talk. Okay. And then I will, so every afternoon they will say they'll feel sleepy after food. So they will ask me to give the talk, and that's how whenever I used to give, they used to give these comments, and that's how I learned the subject. And so by reading and giving the talk, and they will correct me. So that way I learned. And so my first problem, he told that so there was this atmospheric general circulation model which the Kasture group they developed. And we had a computing system also. Those days, now mobile may be faster, mobile phone. So that a computer was there. And Kasture used to run. So I used to go behind him. Kasture, please tell. He will tell only small things. So you have to really extract the information from him. But it was a very, very nice atmosphere. I really learnt a lot from these people. And so they were, there was also Professor B.R. Subbaraya, who's no more. And he was also very interested. So they were thinking to, PRL was planning big those times. And there was a director called Devendra Lal. Professor Devendra is a big name. He went to Scripps Institute of Oceanography. He is regarded as one of the giants in geoscience. So 80s he had the vision that if you want to study climate, you have to have a model that goes not only modeling and observation system that couples the solid earth, the oceans, the atmosphere, go all the way into the ionosphere and beyond. So he had that big vision, and so those were the people, and Professor Krishna Swami. So PRL made a big difference, and they were thinking that not only planet, Earth's atmosphere, you should look at planetary atmosphere. What is happening in because it's a ISRO lab. There's a lot of focus on space science. What is happening to the Martian atmosphere? What is happening to can we study the general circulation of the Venus atmosphere? So and this was the problem my guide gave me after the and people were doing lab experiments those days. As he told, he was telling only 2 things determined. One is the rotation rate, other is the equatorial or temperature gradient. For example, Venus is a very slow rotating planet. And this was the problem. If you go to Jupiter, it is a fast rotating planet. It's much bigger. So it has its own vortices, great red spot. So that was the kind of focus. So my second year report, I was thinking that we will work on the planetary atmosphere. Again, it was not very clear. Like I told you, you read everything. You should learn. And then I decided, no, I will go work on. Somebody told me first you focus on Earth's atmosphere before you go into. That's how it started. Then when it came to Earth's atmosphere, then I focused on the tropics. So my focus, and there were already some good studies on the tropics, landmark studies. And so I decided to focus on the tropical circulations, heat-induced circulations, tropics, which was my PhD thesis, which I submitted here. Then when it came to Earth, so my journey, I got into modeling, numerical modeling and computation. And my guide had worked with, he had visited Geophysical Fluid Dynamics Lab in Princeton in the States, and he worked with Professor Sugihiro Manabe, whom I later had an opportunity. He was Nobel Prize winner in 2021 for the global warming. Yeah. And he had already, and he is the greatest climate modeling person that has is still there. And so Professor Keshavamurthy had worked with him. And I had seen some interview on TV, about climate change, how carbon dioxide is increasing. They had already seen, this was in the late 80s and 90s. So after that, so that's how the journey started. I got into this field. And later on, after I was about to finish my PhD in 1992, I applied for a job in Delhi, NCMR, National Center for Medium Range Forecasting.
Okay.
So I did not know whether I just applied.
Right.
Again, they called me for interview. So I attended. We got selected. I and my senior, Dr. Krishna Kumar, both were selected. So we joined in 92, April 92, Delhi. So I worked there for 3 years. So I did not know. And so I then applied. That was more of an operational type of work, which was good, but it was a different type. It was operational forecasting, and they had the big supercomputer and things. Of course, Delhi weather I was not very happy, and also I had to travel a long distance every day. Then IITM came out with an advertisement. They wanted to start this climate modeling. It was good, but it was a different type. So 1994 I applied, and in 94. The interview was over. First round I was not shortlisted. This one selected, but I was on the waiting list. The other person did not join, so I came in 95. I joined. So now I'll be completing 30 years in IIT, and it's been a fantastic place. And it is a very good research institution. And I never realized that. So when I got my marriage with my wife, she told me, what do you do? I told her I'm working in CMRWF. She told me meteorology is a trap subject. You are giving weather forecast, and they thought initially I may be coming on TV. But I told her I don't come on TV. So, but later on, but that journey. So weather and climate was not a very popular subject at that time. Now, over a period of time, now people are realizing that climate is changing, and they thought initially I may be coming on TV. Affecting everything, all temperatures, now heat waves is affecting human health. So all the ice is melting, sea level, right? So all the extreme events are increasing because of that. So this climate, now people are recognizing that climate change is a real problem.
Right.
So that's how I got into it. And 1998, I had an opportunity. There was a frontier research system for global change in Japan.
Okay.
That's when I got a chance. They invited me, and that was with Professor Manabe's group. He was heading
the Nobel laureate.
Nobel laureate. He was not Nobel laureate at that time. He was in
2021.
So he retired from Princeton, and the Japanese government, they told him they set up this new institute. So he was leading the global warming. And I happened to go, and he was the program director. So below him, the Nobel laureate, he was not Nobel laureate, Dr. Masato Sugi. So I worked with him. So he retired from Princeton, and so working with all these big people like Professor Manabe and all, that is a leading the big game changer. So the people whom you meet in life also matters a lot. Your teachers. So these mentors, they are very important. They can shape your career, your thinking, everything.
So as you mentioned, even now I am not sure how much of awareness is there about the field, because as you said, people joke about it. So even nowadays, like Pune, we have Simla office, right, who tells the temperature. So there's always this joke, why are you carrying an umbrella? Because Simla office said it will not rain today, that means it will rain. So that is how people perceive it. But of course we know there's a serious field now, and as he mentioned, it is become call of the day. Climate crisis, weather crisis, it is affecting everything. Like now it's just February right now, but we are all feeling the scorching heat, is it not? And everyone is saying, oh, this is just February, what will happen till May? Everyone is worried that it's going to be so hot. So it's for real, this whole problem, and it's affecting not just us but the whole world. So it's become a very, very valid field. So if anyone wishes to pursue a career in meteorology, for example, or any related subfield, how should they go about it?
Yeah, so now I think meteorology is there in many courses offered by many universities, including Pune SPTU.
It's become a very, very valid field. So if anyone
People are
wishes to
IITM,
pursue a career in
so one is
meteorology, for
there are a lot of
example, or
opportunities.
any
That's what I
related
want to
subfield, how
show
should
you.
they go about it?
Weather prediction, it is going to stay because you need that. Without the weather forecasting, so we have the IMDs. So in term, people are looking for jobs. IMD is a possibility. Now ISRO will also look for people. National Center for Medium Range Forecasting, IIT. Many institutes and also academic institutions, many IITs are having this program. ISR is having a such program. So it is the field is, there's a lot of opportunity in terms of people are, so that is the immediate thing, what if I learn, where will I go? So in terms of opportunity, it's a plenty. And a field where you are also working with computers, and so you will also gain experience in coding, working with scripts. And now this machine learning, AI has come. So opportunity wise, it's plenty. On top of that, now air quality, air pollution, and so that's also a big issue. So that is also opening up into a big area. Now, when you talk about climate, it is not just the atmosphere. Now, people, that's what Manabe is even in his 60s work. Beyond his Nobel Prize winning work of global warming. So that's also a big issue. He talked about we have to look at the atmosphere, the ocean, the land. You have to look at all the components of the Earth system. If you want to really understand how there is the exchange of energy, momentum across how the circulation develops. And so when you get into that, so there is National Institute of Ocean. So when you go to the ocean, you have the National Institute of Oceanography, National Institute of Ocean Technology. So you are looking at the entire Earth system. Similarly, when you are looking at hydrology, you are looking at soil, what is happening at the land surface, what is the soil moisture, what is the groundwater. So when you go to the ocean, so you have the opportunities are plenty. And now climate change is not only affecting the weather, extreme weather, it is also affecting the biological systems. It is affecting health. It is affecting the ecosystems. It is affecting the organisms, living organisms in the both on the land, in the ocean, and also in the high altitudes. So it's the entire Earth system. So it's a very so the plenty of opportunities.
Correct.
So I think it's the right time. I think I strongly encourage. I think people in physics, they are doing excellent work. Now how to channelize that into these type of applications is very important. So this is probably one of the mistakes. I won't say mistake. This realization was not there in the 80s, late 80s. Physicists, and they were very pure physicists. All this meteorology and all, meteorology. So this kind of, so I think same thing with the mathematics people. They are also, very pure. They want to do this one. They applied mathematics and all is for them low level. So I think that mindset is, to me, may not be there. So you have to now, when you talk about that, it's all integrated, it is interdisciplinary. That's where I think there is a huge opportunity, and we have to cash out that.
So as we all know, interdisciplinary is the word now. We know it, we hear it in different ways, and even like, for example, those who are doing material science, they know about nanotechnology, where everything comes in together, or two branches of science coming together, biophysics or physical chemistry, chemical physics, and so on and so forth. So it is very important, and as he said, That's the norm now. So everyone, earlier there used to be this saying, jack of all trades, master of none. So I always tell the students that be jack of all trades and master of one. So you have to be master of one, but you need to know about other subfields also. So it's very important in that sense. Could you tell us about IITM? So everyone,
so IITM is of course now one of the, it's a very big, very famous institute. We have completed 60 years.
And master of
63, we are now 63 completed.
63
years.
Other subfields also.
It's
So it's very
institute
important
of
in that
national
sense.
eminence.
Could you tell us about IIT?
Over the 63 years, it has done wonderfully. And it is a unique institute for tropical meteorology worldwide.
Oh.
Okay, so this is in Pune, and this was based on the recommendation of the WHO, and started by another visionary, Professor Vishareddy. And so this campus we moved in 1988. Earlier we were in the IMD's Ramdurg house. And basically the way, whatever research, because IMD is an operational institute, and this was envisioned for research. So whatever research you do in IITM should help IMD to improve the weather and forecast. So this was the end. This, I think people have been, they kept on doing good work. And over a period, I think in 2000 we were earlier, before, now we are presently in the Ministry of Earth Sciences. Earlier we were under DST, and earlier even before that we were in the Ministry of Civil Aviation and so on. So now it's fully under, once we came under MOES, a lot of funding came. And so we could upgrade our HPC. We have the high performance computing. We have the best, we have the fastest computer at IS India, which is at IIT, in the top 500 list. And it's about kind of 22 petaflops. This plus NCMRW put together. And we have also AI systems. And so I think when Professor Keshavamurthy came, he placed emphasis on climate modeling when he started that.
Right.
So that was a very important thing. This is 93, 94, a small group on climate modeling started. So that was good. At that time when he started, today we are able to contribute to climate change assessment for the IPCC report. IITM model is going from our group. Okay. So it's a big contribution that is coming from India, from IITM. And not only they are also doing, there's a program on monsoon prediction, seasonal forecasting, and sub-seasonal forecasting. There's work on atmospheric lighting and atmospheric electricity. There's work on boundary layer process. There are studies going on air quality forecasting. That is also being done for the Delhi, because Delhi in winter time there is a problem of air pollution.
Right.
Those forecasts are made from IITM. And now we have a lab in Mahabaleshwar called High Altitude Cloud Physics Lab. So that's also an IITM campus. Now we have one more in Bhopal, a place called Silkeda, Central India. This is atmospheric research test bed. So in the future we are thinking that Silkeda will become a very, maybe another 15 years down the line, it will be another important facility. It's a 100-acre land there. So IITM has also spread its wings. We have a small branch office in Delhi. We have done work on cloud seeding, where people have flown several hours away. So if you do the cloud seeding, what is the feasibility of training? So that also was done by IITM. So IITM works on several areas, vast areas, on theoretical studies, and so both observation and we have some of the best radars in the country in IITM, and all kinds of instruments, whether you go to high altitude cloud physics lab. There's also one facility in Solapur. So IITM has spread its wings everywhere and working on all aspects of the coupled system, climate system, weather and climate scales. Slowly, I think they are also getting into this machine learning and digital twins and so on. So I think it is, opportunities are huge. And I think I understand that Pune University is also wants to start a climate science program. Maybe I don't know whether I should reveal or not. Climate science and action, which we will be very happy to support. Ministry maybe is very much inclined to support. And because this is the right ecosystem in Pune. You have the PPU is there, and then ISER is there, and all the research institutes, IITM, NCL, ERDs, CIDA, and we have here Ayuka, GMRT, all within a all the defense labs here, all within a very, very small area. I think that gives a big advantage. In some areas, in some cities like Bangalore, there are good institutes, but one problem is the traffic and the long distance. So that you have a big problem. But Pune, I think it's the ecosystem is fantastic. And NCL. So all I think that knowledge is in a very small area. That gives a big advantage. And as I said, for this interdisciplinary science and things, I think that is going to be the key, how we are going to address. Because everything this AI starts taking over, then we are in trouble. So I think what is really important is how we work as a community, how you address the grand challenges of the community. And there's also this Pune Knowledge Cluster, which is PKC, which is there in Ayuka. So I think having all this resource and all this ecosystem in a small area, I think scientific ecosystem, also cultural ecosystem is fantastic. I think that gives a big advantage. And so my experience in IITM is amazing. It's a great institute. I had great friends. My team was fantastic. I have students with whom I worked, and they were all so that building that whole ecosystem. And we have the Indian Meteorological Society Pune chapter. They are among the best. So I think so when we think about all these things, it's a great place. And also Pune, I have a special affection for the Pune student, Pune University student.
So like he mentioned, we have our IPA chapter here, right? I'm sure all of you who have attended the function on every 5th of September, I mean, whenever you studied here. So IPA, Indian Physics Association, Pune chapter is right here. So as he mentioned, right now you all are here in an education and R&D hub. So please take advantage of it, as you can realize how many institutes are there in, say, a few kilometer radius span. So we are in the university, there's NCL, there's IITM, there's Ayuka right on the campus, there's NCRA, there's ISER Pune right there. I mean, please take advantage of this situation that, as he mentioned, you are in a great ecosystem right now here. So if any of our students wants to join IITM, for example, then what should be the path? Like he or she has to do a PhD in physics, or I mean, are there any eligibility criteria particular, or how is it?
Yeah, so normally we advertise some positions every year. We take typically about 15 students on a knowledge basis. Some of them come from Pune University as well. So there is a written test and then we interview. And if they have qualified, because we give fellowship, so one of the criteria is they should qualify UGC NET. Not GATE, UGC NET is very important. And also CSAR also we consider. So if they have qualified, then they get the fellowship and they have to attend the interview. And so I strongly encourage, please visit IIT. And physics students are also, many physics students, they apply. Physics is their chemistry, mathematics. But some mathematics is important because there are people with hardcore, biological science who have not done computation. So that, I don't know whether that is there in the eligibility criteria. But physics is definitely there. So that's an important opportunity. And so in terms of computational infrastructure and our hostel facility is also excellent. And now recently there's a new program called Mission Mousam from the Ministry of Earth Science, which was launched by our Honorable Prime Minister. It's a big program, and so it's going to. So they want to really the local scale forecasting how to improve, and also they are thinking of weather modification research. So that's where all this your advances in physics and technology, and so it will be very important. So we should really take advantage of this opportunity, and IITM is leading that Mission Mosam activity.
So Mission Mosam, I think everyone should take note of it. You can later Google for the name to get some more information. And as he said, so you all are eligible to enter IITM if you pursue that path. You all are already doing physics here. So because that is a big question, right? Everyone, what about the job? Because anyone, if we tell them that, okay, you come for doing masters in physics, first thing they'll ask us, what about the job? What opportunities do we have? So as he is mentioning, there are several opportunities in the field. So I hope everyone is taking note of it, that okay, where all you can go. Because some typical specializations everyone is aware of, but I really wonder how many people knew about, say, for example, this Mission Mosam, that there's something like that which you all can look at, and it's very close by, as he mentioned, so you all can just go and have a look. And nowadays with internet you have websites, so you can collect so much of information even online. So with Sir's vast experience, actually this interview can go on for a very long time, but I can see the organizers, the main volunteers here, and I know that there's a valedictory function planned, and one should never stand between prizes and people, right? So those who presented posters and orals, and now they are wondering, okay, who would win the prize? So we will not let that the suspense stretch too much. So that is why we'll wind up, otherwise this can just go on, this interview. There's so many things Sir can tell us with his vast experience. So in the end, what message would you like to give to all the students? Who would win the prize? So we will not let that
lot of opportunities for innovation.
Stretch too much.
I think that is going to,
So
because
that is why
the
we'll
challenges we are
wind up,
facing today, whether it is climate change,
there's so many things Sir can tell us with his vast
security
experience.
issues,
So in the end, what
the kind of
message would you
pollution,
like to give to
whether,
all the students?
so if you want to deal with these big issues, I think we have to work together. Innovation is going to be key, and new ideas and working together is going to be a very important thing. And by the way, we have also a lot of project positions in IITM.
Please take a note.
Project scientists, about almost 200 people are there. Apart from the regular employees, 200 project scientists. So opportunities are coming, a lot of opportunities. So I strongly encourage people. By the way, we have also a lot of eyes open, even in the high performance computing, AI infrastructure, things. Apart from
So AI, I mean, as we even earlier we were discussing, both of us. So we said that nowadays students feel that only, I mean, many students feel that only if they do a career right in AI or ML, only then they get acquainted to that. That is not the idea. You can use them as tools. So you can pursue pure science subjects, and you can use AI as tool. So in that way you will have best of both the worlds. You learn pure science as well as you are using AI, so you also get to do what you want that way. So I think that will be the right approach. So you can pursue
here we already have the biotech groups in Pune University.
And you can
So this climate will be a very important thing where all the departments,
you will have best of both the worlds. Learn pure science as well as you are using AI, or you also get to do what you
integrated,
that way.
collaborate with all the research institutions. I think Pune will be a fantastic thing. So there will be many opportunities, and we can really contribute in a big way. Because now China is growing very fast. If you want to make something, Pune is the place. And SPPU and ICER and these people, I see a big opportunity, fantastic thing.
China is deeply seeking everything. Everyone knows about it, right? Deep seek is the key word now. Wherever you go, people are worried and they go, what Deep seek is going to do? Chat GPT is just... So, but he has mentioned that Pune is full of very good opportunities. So please remember that look at the optimistic side and try to find out more information about whatever you heard today. And main thing is that spirit, right? Like earlier when he started with the interview, that there are going to be difficulties, but it's how you look at those difficulties. What is your perspective? That is what finally is going to matter. So be there AI or no AI, or be there computers or no computers, still this philosophical journey will always remain valid. So through these interviews, that is the idea. So that's why this is never a technical talk, because entire conference you've heard a technical talk. Several technical talks rather. But here you get to explore a career of a very senior scientist, and then you can make notes for yourself that okay, if you wish to pursue it, how will you go about it, right? So thank you so much for taking out time from your busy schedule. He's a director, so very, very busy. But for you all, he has taken out time, and I'm sure we admire.
Thank you, everyone.
Thank you, Dr. R. Krishnan, sir. Your profound and thought-provoking interview, your expertise and the depth of knowledge shared today will undoubtedly provide the student with invaluable lessons. Your perspective in your life and academic both will offer priceless guidance in our career. We truly appreciate your time and wealth of information you have imparted. And I heartfelt thank you to Dr. Dipti ma'am for skillfully hosting today's interview. Your thoughtful questions and engaging conversation with our guests have made this session truly insightful. Now, may I request Professor Banpurkar sir to honor Dr. R. Krishnan sir. You have imparted. And I heartfelt thank you to Dr. Dipti ma'am for skillfully hosting today's interview. Your thoughtful questions and engaging conversation with our guests have made this session truly insightful. Now, may I request Professor Banpurkar sir to honor Dr. R. Krishnan sir. You have imparted. And I heartfelt thank you to Dr. Dipti ma'am for skillfully hosting today's interview. You have a RAMAN in thoughtful questions and engaging conversation I request Miss Swara to honor Dr. Dipti ma'am. I request Miss Swara to honor Dr. Dipti ma'am. So this is a short video what we have do in 2 days of RMC. this is a short video what we have do in 2 days of RMC. So this is a short video what we have do in 2 days of RMC. A huge thank you to our talented videographers and photographers for capturing the beautiful memories of the 2 days of RMC. Your work helped us relive these special moments. Thank you. A huge thank you to our talented videographers and photographers for capturing the beautiful memories of the 2 days of RMC. Your work helped us relive these special moments. Thank you. A huge thank you to our talented videographers and photographers for capturing the beautiful memories of the 2 days of RMC. Your work helped us relive these special moments. Thank you.
Yes. Good evening everyone. A warm and cordial welcome to the valedictory function of the 31st Raman Memorial Conference 2025. This prestigious event organized by the student for the student has been an inspiring journey into the fascinating world of quantum science and technology. It has been an enriching experience with thought-provoking discussions, groundbreaking research presentations, and insightful deliberations from esteemed speakers and enthusiastic participants. As we come to the closing moment of this remarkable conference, let us take a moment to celebrate the knowledge and collaboration fostered here. To begin this session, we are honored to have with us a distinguished guest and esteemed faculty members. We extend our heartfelt gratitude to Dr. R. Krishnan Sir, Director, Indian Institute of Tropical Meteorology, Pune, who has graced us with their presence. We also extend a warm welcome to Professor Banpurkar Sir, our esteemed faculty members, respected professors, and dear students. Your presence makes this occasion truly special. I request our dignitaries, Dr. R. Krishnan Sir, Professor Banpurkar Sir, Professor S.I. Patil Sir, and Chairperson Ms. Anupama to kindly come forward. Our esteemed faculty members, respected professors, and dear students, your presence makes this occasion truly special. I request our dignitaries, Dr. R. Krishnan Sir, Professor Banpurkar Sir, Professor S.I. Patil Sir, and Chairperson Ms. Anupama to kindly come forward. Our esteemed faculty members, respected professors, and dear students, your presence makes this occasion truly special. I request our dignitaries, Dr. R. Krishnan Sir, Professor Banpurkar Sir, Professor S.I. Patil Sir, and Chairperson Ms. Anupama to kindly come forward. Our esteemed faculty members, now, to reflect upon the journey of past few days, I invite Ms. Anupama Kadam, a chairperson of 31st Raman Memorial Conference, to present a brief report on the conference proceedings.
Good evening all.
Now, to reflect
Respected
upon
Chief
the
Guest,
journey of past
Dr.
few
R.
days,
Krishnan Sir,
I invite Ms. Anupama
Professor
Kadam, a
S.I. Patil
chairperson
Sir,
of
Head of the
31st Raman
Department,
Memorial
Barpurkar
Conference,
Sir,
to
esteemed
present a
speakers,
brief report
distinct
on the conference
delegates,
proceedings.
faculty members, research scholars, and dear participants. Good evening, all of you. As we reach the conclusion of 31st Raman Memorial Conference, I stand before you with immense gratitude and pride. Over the past 2 days, we have witnessed and enriching the exchange of ideas, groundbreaking research presentation, and insightful discussion on the theme quantum science and technology. This conference has successfully brought together some of the finest minds in the field of physics, fostering collaboration and igniting new research direction. The engaging keynote address by P.S. Anil Kumar Sir, technical session and interactive discussion have undoubtedly deepened our understanding of quantum science and its technological application. I extend my heartfelt thanks to our Dr. R. Krishnan Sir, Director of IITM Pune, for gracing this occasion and sharing their invaluable insight during the interview session. Your presence has truly elevated the height of this event. I would like to express my sincere gratitude
to Professor Banpurkar sir for their unwavering guidance and leadership in making this conference and grand success. Your vision and commitment have played a crucial role in shaping this event. A special thanks to our Head of Department of Physics, Professor Sanjay Dhole sir. He could not be with us today due to their family commitments, but his unwavering support and continuous guidance from the very beginning to final moment of this event has been instrumental in success of this conference. Over the past 2 days, I am delighted to share with you that our conference has featured 7 invited talks, 32 oral presentations, 85 poster presentations, and with more than 200 participants in the event. I firmly believe that each oral presentation, poster presentation, and session, including the invited talks, will significantly contribute to participant knowledge of physics, quantum science, and their respective fields. The exchange of ideas, insight, and research finding has truly enriching, and I am confident that each of these conference will have lasting impact on understanding of quantum science and technology. Now, I would like to take a moment to express my heartfelt appreciation towards my committee members. I must say that without their unwavering dedication, tireless efforts, and exceptional teamwork, this conference would not have been the resounding success it has. Each and every committee members had worked tirelessly, effectively pouring their heart and soul into every aspect of the conference. Their commitment to excellence has been truly inspiring, and I am deeply grateful to their contribution. A special vote of thanks to our sponsors, Bank of Maharashtra, SBI, Indian Institute of Topological Metrology, Pune, Tradpro Technologies, NCRA, Sharad Agency, Pune Knowledge Cluster, Litex, whose generous support has been vital in making this event reality. Your belief in our vision and contribution have played a crucial role in providing environment that fosters learning and innovation. I also thanks to Indian Physics Association Pune chapter for their support. I would like to extend my heartfelt appreciation to our secretary Swati Rane for her dedication and commitment in overseeing every aspect of this event. Organizing conference of this scale requires immense dedication, teamwork, and meticulous efforts. I take this opportunity to extend my heartfelt appreciation to incredible members of our organizing committee who work tirelessly to ensure the execution of this event. I would like to thank Ms. Swati Rane, Mr. Somnath Ladhane, Treasurer, Akash, Swaranjali, Reshma, Nazmeen, Amol, Sunil, Pooja, Jyoti, Mansi, Tanuja, Sandhya, Nikita, Swapnali, Monica, Pranjal, Suman, Shushankar, Vivek. Each of you played a crucial role in making this RMC 2025 a successful. Your dedication, hard work, and teamwork were a driving force behind the smooth contribution and execution of this event. I sincerely thanks to all of you, your efforts and commitments. With this, I would like to thank our All India team and cultural team for their dedication, support, and for their enthusiastic performance. A driving force behind the smooth contribution and execution of this event. To our young researchers and students, your enthusiasm and curiosity have been a true driving force of this conference. I hope the knowledge shared here will inspire you to push the boundaries of scientific exploration. Sir, before conclude, I would like to take a permission to express my feeling in Marathi. So this is the closest language, so we can express our feelings in Marathi. So before I think 1.5 month we meet here for the meeting of the RMC. सो त्यावेळेस असं होतं की सर इथे बसलेले डोले सर होते बनपूरकर सर होते मग ते सर होते सगळे आणि असं होतं की आता RMC घ्यायचंय आणि कोण कोण हे करणार सगळे PhD स्टुडंट इथे बसलेले होते असं होतं सगळ्यांचं नाही आता मी नको तू असं चाललं होतं त्याच्यानंतर मग सगळ्यांनी एनकरेज करून आमची 21 मुलांची टीम झाली त्याच्यामध्ये मग सगळ्यांच्या एनकरेजमेंट नंतर मी ॲज अ चेअरपर्सन स्वाती ॲज अ सेक्रेटरी सोमनाथ
ॲज अ ट्रेजरर आणि सगळे ऑर्गनायझिंग कमिटी मेंबर्स. सो पहिल्या दिवसापासूनच आमचं असं होतं की आज मीटिंग झाली 12:30ला, 3 वाजता लगेच आमचं की आता प्लॅनिंग डिस्ट्रीब्युशन ऑफ दी वर्क, की आता हे टीममध्ये हे लोक असतील, ह्या टीममध्ये हे लोक असतील. पहिला एक 8 दिवस की आपल्याला फंडिंगसाठी इन्स्टिट्यूट शोधायच्या, त्याच्यानंतर स्पीकर्स हे करायचे, तर की जे थीमला मॅच होतील असे स्पीकर्स पाहिजे होते आम्हाला. मग सगळ्या मुलांनी मिळून स्पीकर्स हे केले, इन्स्टिट्यूट्स झाल्या की ज्याच्याकडे आम्ही फंडिंग पाठवतोय. मंथ डिसेंबर नंतरचा होता, त्याच्यामुळे असं होतं की सगळ्या इन्स्टिट्यूटचं की ऑलमोस्ट त्यांचे फंड संपत आलेले, त्याच्यामुळे मुलांचंही थोडंसं टेन्शन होतं. पण सगळे स्टाफ आणि टीचर्स हेड त्यांनी खूप आम्हाला सांभाळून घेतलं. त्यांनी सांगितलं की नाही, तुम्ही फक्त कॉन्फरन्सवरती फोकस करा, की फंडिंगचं टेन्शन घेऊ नका. त्यातूनही जे ऍडजस्ट झालं ते त्याच्यानंतर डिपार्टमेंटचं सपोर्ट्स. ऍक्च्युली ही कॉन्फरन्स आपण म्हणतो ऑर्गनाइज बाय द स्टुडंट फॉर द स्टुडंट, बट विदाउट द हेल्प ऑफ टीचर्स दिस कुड नॉट बी हॅपन. सो आय वुड लाईक टू थँक्स ईच faculty members, heads, non-teaching staff, administrative staff for their support from the day. So, कॉन्फरन्स आपण म्हणतो ऑर्गनाइज बाय द स्टुडंट फॉर द स्टुडंट. नंतर फंडिंगचा प्रश्न सॉल्व्ह झाला, त्याच्यानंतर आमच्याकडे प्रश्न होता लंच डिनर. त्याच्यामध्ये झाले केटस फायनल झाले. त्याच्यानंतर मग अमोल सरांच्या मागे टेन्शन होतं की मग आता ते बिलिंग वगैरे. 2 दिवस कॉन्फरन्स होती. अमोल सोनवणे कॉन्फरन्सच्या आतमध्ये नव्हते, ते फक्त सगळ्यांचं लंच, फंडिंगचा प्रश्न सॉल्व्ह झाला, त्याच्यानंतर डिनर, बाहेर प्लेट्स किती लागल्या, किती गेल्या, किती राहिल्या यातच काउंट ते करत होते. आणि आज पहिल्यांदा ते इथे बसले, तिथे फोटोग्राफ्स होते, त्याच्यानंतर फोटो नव्हता त्याच्यासाठी की तो बाहेर होता. आणि त्याच्या एफर्ट्समुळे की सगळे लोक व्यवस्थित सगळ्यांचं डिनर लंच सगळं पॉसिबल झालं. सो थँक्यू अमोल. स्पेशल थँक्स नाजवीन अँड रेश्मा की जे फंडिंगसाठी एक महिनाभर ते फक्त त्याच्यासाठीच एफर्ट्स घेत होते की सगळीकडनं फंडिंग आले की नाही, फॉलोअप घ्यायचा, तिथे पुन्हा कॉल करायचा. सो त्यांच्यासाठी फंड आले नसते तर कॉन्फरन्स पॉसिबल नव्हती. सो थँक्यू नाजमीन, रेश्मा आणि आपले सगळे कमिटी मेंबर्स, स्वरांजली, सुमन, निकिता, पूजा आणि स्वरा. दिवसभर बीसीवरतीच होतं की किती ॲबस्ट्रॅक्ट आले, किती त्यांच्यासाठी. दिस इज आय थिंक फर्स्ट टाइम in Raman Memorial Conference we have received more than 85 poster presentations, 44 oral presentations and more than 200 participants. So हे सगळे सॉर्ट करणे, ॲबस्ट्रॅक्ट इव्होल्युशन करणे आणि प्रेझेंटेशन सगळे लाईनअप करणे हे सगळं स्वरा करत होती. सो थँक्यू सो मच स्वरा की एवढं स्मूथली सगळे ओरल प्रेझेंटेशन, पोस्टर प्रेझेंटेशन हे झाले. थँक्यू सो मच. अँड लास्ट आवर कल्चरल टीम फॉर द MSc. सो दिस इयर आम्ही बाहेरून कल्चरल टीम मागवली नाही. आपलेच MScचे मुलं की ज्यांना ॲप्रिशिएट करावं, त्यांच्यातलं टॅलेंट कळावं सगळ्यांना, त्याच्यासाठी आपण त्यांना चान्स दिला होता. त्यांनीही खूप छान कल्चरल प्रोग्राम इव्हेंट केला. तेही आता समजतील थोडंसं की टायमिंग कसं फॉलो करायचं हे त्यांना. इव्हेंट खूप छान झाला, सगळं परफॉर्मन्स खूप छान झाले आणि त्याच्यातले टॅलेंट सगळ्याच इथल्या बसल्या ऑडियन्सला कळाले की कळावं सगळ्यांना. आपण त्यांना चान्स दिला. स्टडी बियॉन्ड द स्टडी की ते अजून त्यांच्याकडे काय काय आहे ते सगळ्यांना त्यांनी दाखवलं. त्याच्याबद्दल थँक्यू सो मच. And lastly, I would like to thanks all the participants for their presence, their presentations, orals. Thank you so much. Study beyond the study. ते अजून त्यांच्याकडे काय काय आहे ते सगळ्यांना त्यांनी दाखवलं. त्याच्याबद्दल थँक्यू सो मच.
Thank you, Anupama ma'am, for giving us a concise yet comprehensive summary of the conference. It is truly incredible to see the dedication and hard work that went into making this event a grand success. I kindly ask few of you to share your feedback, as your feedback will be greatly appreciated. Yes, it is truly anyone from you. Please share your feedback, dedication and hard work. Can you come forward? Making this event a grand success. I kindly ask few of you to share your feedback, as your feedback will be greatly appreciated. Yes. anyone from you. Please share your feedback.
Good evening, everyone. The experience was great. I've been studying here in same department, but this conference gave me confidence that I can showcase my talent other than physics, of course, and physics also. But it gave me exposure to communicate and explore around the department and talk to PhD students and my seniors. And it was a great experience. Thanks to all the seniors and PhD students too. And thanks to our Banpurkar sir for giving us this opportunity. The whole experience was nice, and I had a great time here and got a lot to learn about. I attended few oral presentations also, and they were like giving a direction to me that how I can go ahead if I want to work in this. And now I have become more interested in research. So thank you everyone for this experience.
Oral presentations also. Thank you for sharing your feedback. Yes, anyone else want to share your feedback
to me that how I can go ahead.
Okay.
If I want to
Every great
work in
event
this, and now
is backed by a team of passionate individuals. It's time to recognize and appreciate the relentless efforts of our organizing committee. I request Professor Banpurkar sir, head of the Department of Physics, to present a token of appreciation to our esteemed guests. It's backed by a team of passionate individuals. It's time to recognize and appreciate the relentless efforts of our organizing committee. I request Professor Banpurkar sir, head of the department. Now, finally, we have arrived at the moment we have all been waiting for, the announcement of result. I request Ms. Tanuja to kindly announce the winners. Thank you. Now, finally, we have arrived at the moment we have all been waiting for, the announcement of result.
On behalf of organizing committee, I kindly request
I request Ms. Tanuja to kindly announce the winners. We have arrived at the moment we have all been waiting for, the announcement of result.
on behalf of organizing committee, I kindly request
I request Ms. Tanuja to kindly announce the winners.
On behalf of organizing committee, we warmly welcome you to the prize distribution ceremony of the exciting conference. We have witnessed an incredible exchange of ideas, presentations and discussions over this conference event, and now it's time to recognize and celebrate the outstanding contributions. From the oral prizes, from the UG and PG poster presentations, the first prize is going to Mehendi Chanda Khede.
incredible exchange of ideas, presentations and discussions over this conference event, and now it's time to recognize and celebrate the outstanding contributions. From the oral
She is
prizes,
from Ferguson College.
and PG poster presentations.
Second prize goes to Joshi Pratiksha from SPPU.
Exchange of ideas, presentations and discussions over this conference event, and now it's time to recognize and celebrate the outstanding contributions.
Third prize go to Harshavardhan
She
Dangre.
is from Ferguson College and PG poster presentations.
Second prize goes to Joshi
Harshavardhan
Pratiksha
Dangre
from SPPU.
Exchange of ideas, presentations and discussions over this conference event, and now it's time to recognize and celebrate the outstanding contributions.
Third prize go to Harshavardhan Dangre.
College.
Harshavardhan Dangre, National Institute of Virology.
Second prize goes to
Harshavardhan Dangre
from SPPU.
Now the posters from research scholars. First prize goes to Vaibhavi Gulavani
Harshavardhan Dangre
from Ferguson College. Second prize goes to Prasanna Lohkar, IITM Pune. Now the posters from research scholars. First prize goes to Vaibhavi Gulavani. Acha. Third prize goes to Akash Vispute, SPPU. Second prize goes to Prasanna Lohkar, IITM Pune. Now the oral prize presentations. The first prize goes to Miss Amruta Lohar from SPPU. Second prize goes to Monica Zavle from IIT Bombay. Now the oral prize presentations. The first prize goes to. Is there anyone from SPPU? Okay. Third prize goes to Shruti Shah from SPPU. Second prize goes to Monica Zavle from IIT Bombay. Now the oral prize presentations. The first prize goes to. Now the thesis presentation prizes. First prize goes to Swati Rahane from SPPU. Third prize goes to Shruti Shah from SPPU. Second prize goes to Monica Zavle. Second prize goes to Vaibhav Valve from ISER Pune. Now the third prize for Sandhya Ghadge from SPPU. First prize goes to Swati Rahane from SPPU. Second prize now the Damle prizes. Oral presentation goes for Soranjali Shinde from SPPU. Now the third prize for Sandhya Ghadge from SPPU. And for the poster, it's Amey Sunil Mahadi from SPPU. Now the Damle prizes. Oral presentation goes for Soranjali Shinde from SPPU. Now the third prize for Sandhya Ghadge from SPPU. And for the poster, it's Amey Sunil Mahadi from SPPU. Organizers. Now the Damle prizes. And the last one, Bhide prize, is for Nikita Kapadi from SPPU. It's Amey Sunil Mahadi from SPPU. Congratulations to all the winners. And the last one, Bhide prize, is for Nikita Kapadi from SPPU.
Moving forward, we now invite our esteemed chief guest, Dr. R. Krishnan sir, Director of IITM Pune, to share their thoughts with us. We are eagerly look forward to your words of wisdom. Moving forward, we now invite our esteemed chief guest, Dr. R. Krishnan sir, Director of IITM Pune, to share their thoughts with us.
Thank you.
We are eagerly look forward to your words of wisdom.
Professor Patil. Dr. Anupama, sorry, and all the esteemed colleagues, Dr. Deepthi and all my esteemed colleagues and friends. First of all, I want to congratulate all the students of this department, physics department, for organizing this beautiful event. So I'm very happy to know that this whole program is organized by only students and all the esteemed. So first of all, congratulations and thank you very much for inviting me. And it's nice to see so many young people getting recognition, and this spirit is very, very important. And we have to keep this thing going on. And I'm so glad that you have completed 30 years. And IITM will support this, well, I'm sure, in the coming years. And we should enhance, we should keep doing this. And we'll also strengthen our collaboration with IITM, whatever possible way. It is very, very and we have to keep this. As I said, this ecosystem is fantastic. We should really use it to take advantage of this to address bigger problems we are facing. And so many young people, so many talented people are there. That is our real strength. So let us work together, and please let us know in whatever way we can support you or we can use it. And so very happy to do that. Yeah, I see overall it's a positive atmosphere, and this is what so many talented people are there. That is our real strength. So thank you very much, and wish you all the best. Work together. Future. Please let us know whatever ways we can support you or we can use it. And so very happy. packages. That's what the speaker. Yeah, I see overall it's a positive atmosphere, and this is what the talented people are there. That is our real strength. So thank you very much.
Thank you, sir, for your amazing talk. Now, as we approach the conclusion of this remarkable event, I invite Ms. Nazmin to deliver the vote of thanks. Thank you, sir, for your amazing talk. Now, as we approach
Before
conclusion
vote of
of
thanks,
this
I would like
remarkable
to
event, I
thanks
invite
to our
Ms.
sponsors.
Nazmin to deliver
So
the vote of
I
thanks.
request okay, I request Pratiksha to call the sponsors for the felicitation.
As we approach
Before
conclusion
vote of thanks, I would like to thanks to our sponsors. So I request
I request
Pratiksha
Managing
to,
Director
call the sponsors for the
Radpo Technology to please be present on the stage.
Vote of thanks, I would like to thanks to our sponsors. So I request
And Ashish Thorat from the Litex.
felicitation.
Radpo Technology to please be present on the stage.
Vote of thanks, I would like to thanks to our sponsors. So I request
And Ashish Thorat from the Litex. Radpo Technology to please be present on the stage. And Ashish Thorat from the Litex. Radpo Technology to please be present on the stage. And Ashish Thorat from the Litex. Radpo Technology to please be present on the stage.
I would like to share that these the sponsors are the students from our department. So thank you everyone. I would like to share that these the sponsors are the students from our department.
sir, for
thank
to
you
give us
everyone.
your few words for concluding.
Okay, good evening. And this is last but not least point I would like to mention. Professor Krishnan, today's guest of the valedictory function. Professor Patil, my dear colleague, friends, and dear student and participants. Okay, I am here in let us say two capacities. Okay, currently I am not HOD. Yeah. I am just keeping a, for example, everything is done by Professor Dhole. Okay, yesterday also I also mentioned the same thing. Because of his busyness or some other work, he put a torch with me and he said that okay, bhago, hame tumhare piche aise. Okay, and then that's one point. Another point is that I actually pointing out since beginning of the conference up to end. Okay, this is truly run by Department of Physics student. Okay, because yesterday's chief guest was Professor P.S. Anil Kumar. He was also a student of this department, and valedictory function. Our guest is also from the Department of Physics. He did a PhD because he has a PhD from this Department of Physics. Okay, yeah. So yeah, and sponsor are also from the Department of Physics. Okay. Yeah, so even in actually my case it's a different. I'm also because I noticed this conference when I joined this department in 1994. So from that point, even I am in the working in the different capacity. So in one feet is actually student feet, and another feet is just kind of administrative feet. Okay. So that's that is the another point. So even because we always the tradition of the department is that we because one of our senior professor has mentioned that okay. Physics departmentचा पाया कोणत्या भटजीने भरलं माहित नाही पण नेहमी it is ever growing because Professor Gupte she I think in 1994 or 1995 she joined from this department to IIT Madras, okay, and then I think for one of the PhD Viva she came and actually mentioned okay जसं तसंच आहे काही problem नाही, okay, and then she literally pointed out that okay physics department will be remain evergreen, okay, so we feel that it will remain evergreen, okay, and this tradition should be continued, okay. Another point is that the motto of the RMC maybe some participants might be get discouraged of some odd questions, okay, but actually motto of this RMC conference is actually different, okay. Question and answers are asked by student or asked by a faculty member is not it is not to just like a discourage or to demoralize and to evaluate, okay, but they are testing that घडा कसा पक्का झाला, so they always test that okay I पक्का आहे की नाही, okay, कुठपर्यंत जाऊ शकतो, okay, असं आहे. So don't be say that okay sir बहुत खडूस आहे बहुत question पूछते हैं, okay, so don't say that in that sense, okay, or because if somebody is asking some question there is actually a point actually you might have missed that point, so you should after that you should sir literally what you are asking that what do you mean for that, what is actually purpose or what how I can think on this question, so you should literally actually point it out that okay question there is some serious good thing is happening, okay. Apart from this conference if you are presenting elsewhere and they are asking the question, so their purpose is different, they should test it that okay how good you are to their institute, so their even outside this Raman conference, the question and answer session is different, but the question and answer session in the Raman conference is totally different. So you should take a positive whatever is the question and answer to the Raman conference, because the motto of the Raman conference is to make you strong, so that you are stronger, because stronger means you can defend in any platform in the world, okay. And this is really maybe you might have been witness Professor Dr. Paubake and everything. These are the students from this department, and you might have been realize that okay what is the let us say the practice of this let us say stage is how useful while presenting elsewhere or even working in the international laboratory. That's another point. And this is really training is important because we inculcate the training, and even every student mentioned that right from MSc training question and answers in the experiment, because Adi sir is not here, he is famous for let us say asking very let us say questions, very big questions and very basic questions, and then after that he used to also answer each and every point whenever you meet in the spirit, okay. So that's important point. Networking is one more important point. Whenever you are presenting poster, okay, most of the people actually taking let us say your extract, okay. So sometimes even international poster presentation you should try to present a poster, because you will get enough time to discuss with a networking is faculty or person, okay. Sometimes in the international conference there is actually a sound bit before the poster. What they do, they actually present their let us say abstract in a let us say 30 seconds. So they come, they present on a stage, they say that okay we are presenting such kind of a poster, if you wanted to see that work come to poster number 30 kind of thing. So it is a kind of a row, and even I have did it in Netherlands, so that's also practice. So poster is also good because you will get enough time to interact with the faculty or students and everything. So networking is important. For example, somebody is doing good work or somebody is doing some calculation, so and someone is actually literally wants that such type of a calculation, they can build up networking. So networking is important issue, and it's also develop a future opportunity. For example, someone is doing some calculations or some let us say theoretical thing, and he is stuck up with these things, okay, and someone is doing very good experiment, okay. so they can have a good opportunity for a future work. Or even somebody is suggesting that, okay, ye karke dekho. That's also a good point in making that kind of thing. Okay. So with this 5, let us say, important point, I would like to conclude, and I wish that this torch, which is actually, because another point, because this year is a 200 plus participant. That's a great thing about this 31st conference, Raman conference, and that's we should actually give them a 3 cheers for the RMC people. Yeah, that's a good point for this 31st conference. Another point, because this year and yeah, this is from my point of view. I wish all the best for participants for good success and good success. Okay, thank you very much. Give them a 3 cheers for the RMC people. Yeah.
Thank you, sir. Now, I invite Ms. Nazmin to deliver the vote of thanks.
Yeah, this is from my point of view. I wish all the best for participants for good success and good success. Okay, thank you.
Respected dignitaries, distinguished guests, professors, and dear participants.
Thank you, sir.
Very good evening. As we come to conclusion of this insightful and enriching conference, it is my honor to deliver a vote of thanks on behalf of Organizing Committee, Department of Physics, Savitribai Phule University. First and foremost, I extend our deepest gratitude to our Honorable Vice Chancellor, Professor Gosavi sir, whose unwavering support and encouragement have been instrumental in making this event possible. A special note of appreciation to our Pro-VC, Professor Parag Kalkar sir, taking the time for the inauguration function and for extending valuable support. A special thanks to our HOD, Professor Sanjay Dole sir, for providing time to time invaluable guidance, and his constant support is the driving force behind this successful event of RMC 2025. I also thank Professor Banpurkar sir for leading these 2 days and providing guidance on time to time. We are also immensely grateful to our distinguished speakers for sharing their expertise and knowledge. The presentation and discussion have been incredibly informative and engaging, offering us new perspective and ideas. A special thank to Dr. Krishnan sir to taking your valuable time to be part of this insightful session. Your inspiring journey and words of encouragement have greatly motivated all of us. A heartfelt thank to our professor whose continuous encouragement, advices, support have added kinetic energy to this RMC. Our sincere appreciation goes to our sponsor whose generous support have made this event possible. Your inspiring journey and we also extend our appreciation to the administrative department, non-technical team, teacher, technical staff, administrative staff, caterer team for their behind-the-scene efforts. A big thank you to all the participants for your active participation and enthusiasm. Your presence have made this conference truly interactive and enriching. Lastly, I would like to thank the RMC Organizing Committee, all the volunteers for their unwavering support, detailed planning, hard work in ensuring the smooth execution of this conference. Without your dedication, none of this would have possible. In the Raman Memorial Conference, we have embraced the essence of the Raman effect, where ideas, knowledge, inspiration, motivation have been exchanged between us, just as energy is exchanged between light and matter. And for that, I thank all of you from bottom of my heart. Wishing none of this would have possible. In the Raman Memorial Conference, we look forward to see you at next RMC 2026. Thank you. I wish you all a very safe journey to homes. Light and matter. And for that, I thank all of you from bottom of my heart. Wishing none of this would have possible. In the Raman Memorial Conference, we look forward to see you at next RMC 2026. Thank you.
Thank you, all of you. We now invite you all to join us for a high tea at a badminton court. Enjoy. Wishing you all a great day ahead. Thank you. To see you at next RMC 2020.
With this, now I would like to declare the 2 days conference is over. Thank you so much.
Join us for a high tea at a badminton court. Enjoy. Wishing you all a great day ahead. Thank you.
with this, now I would like to declare the 2 days conference is over. Thank you so much.
Join us for a high tea at a badminton court. Enjoy. Wishing you all a great day ahead. Thank you.